Hello, hello. Good morning. Thank you very much. I'm surprised on how many people showed up this morning after the caipirinhas last night. I advised some people that caipirinha is not lemonade. It's a little bit stronger than lemonade. But some people likely did not believe me, so they are not here this morning. Anyway, it's my distinct pleasure to introduce, we have 3 professors that are really experts on Raman spectroscopy. So we are going to learn everything this morning about Raman spectroscopy. It's Professor Paulo Sergio Pisani, a very bright postdoctoral researcher, that's Rafaela here, but she is a real expert in Raman spectroscopy, and my good friend Ben, who is also been working a lot for several years with Raman spectroscopy. So we have about almost 2 hours of Raman spectroscopy today. So I'm going to sit here and learn everything. The idea is that both of you, you're sharing. So after maybe 50 minutes, we have to stop a little bit for questions and answers and a little discussion, and then take over again, 50 more minutes. Then we stop again for questions and answers, and then we have the coffee break. So please remember that if you ask clever questions, you may be able to get a nice Alfred t-shirt, right? So, and the idea is that you don't have to be shy. The idea is really pay attention and ask clever questions, or even questions about things that you did not understand. This is not a congress. This is a school. Being a school, we want the students to be active. I remember last year in December in Wuhan, the students were really quiet. Nobody was asking questions. Really, really quiet, really quiet. In the final day, on Friday, then they started to ask questions. So, because they were shy. So you're a PhD students, you don't have to be shy. This is a school. So if you have any questions, give a hard time to the professors. That's the idea here. So I think now even the caipirinha drinking guys are coming. So let's start first with Professor Pisani. Please, Professor.
Okay, good morning, everyone. The talk about the Raman scattering will be in 3 parts, and my part 1, is about the theoretical foundations. The first question: what's a Raman scattering? Raman scattering is a physical process in which light interacts with matter, and the emerging light have different colors. Color means frequency or energy or wavelength. A little bit greater and a little bit lower than the incident one. It's important to point out the human eyes cannot see this difference. To understand why this happens, we need to remember about some properties of electric field. The force applied on an electric charge due to an electric field is given by this equation. That is important for us here. Electric field applied forces on electric charges. In the case of electric dipoles, electric field polarizes the dipoles. Among several sources, we have electromagnetic radiations, which including visible light, which is a wave distribution. Wave distribution here of magnetic and electric field. So by illuminating the sample, we are applying an electric field on it. When we apply an electric field on material, electric dipoles are formed due to electric forces. That is, there is a macroscopic electric polarization of matter. The polarization and the electric field are related by the polarizability tensor. So this equation here. This equation describes how is the polarization, the relation between polarization and the electric field. If the electric field is time dependent, so the polarization will be 2. However, the polarizability can also be time dependent, leading to a polarization given by a product of two the product of two time-dependent functions. That is a modulation. The time dependence of the electronic polarizability comes from the atomic vibrations in materials. Atoms in solids vibrate around their equilibrium position. Polarization can be induced by the application of an electric field, a laser light, for example. So, the atomic core and mainly the electronic cloud are responded to the electric field. We will respond. However, for visible light, the electric field vibrates at very high frequency, 10 to 14 hertz. So only the electronic cloud can vibrate so fast. The atomic core is still heavy. Still have to respond to this frequency. The electronic polarizability, which describes how the electronic cloud responds to the electric field of the laser, is influenced by the atomic motions. Light is modulated by atomic vibrations. This is a sine qua non condition for Raman scattering. Under laser illumination, the light emerging from the sample at the same frequency of the incident one is called Rayleigh scattering or elastic light scattering, while light emitted at different frequencies is called Raman scattering or inelastic light scattering. At this point, we know already the classical origin of the Raman scattering. Since the elastic Rayleigh scattering is about 10 to 6 times more intense than the Raman scattering, we needed to separate the Rayleigh from the Raman components. To do this, we need a Raman spectrometer composed by the light source, laser, normally, your sample, a monochromator, the light detector. Here, prism means today special diffraction gratings. Raman spectrometer and the FM radio system, where we can hear music system, are very similar. The idea is more or less the same. In the Raman spectrometer, the laser light is generated in the laser tube. In the RFM, the FM radio system, 100 megahertz radio wave is generated by a RF source. In Raman, light incides on the sample and is modulated by the atomic vibrations. In radio wave is modulated by audio wave using a microphone. Like this. In Raman, the modulated light collected by the monochromator is separated in relay, discarded, and the Raman components saved transmit to the detector. In FM radio, the modulated FM radio wave collected by the receiver is separated in radio, discarded, and the audio components saved transmitted to the speaker. A simple example, the carbon tetrachloride molecule have four vibrational modes shown here. Two bending modes and two stretching. The corresponding peaks in the Raman spectrum are shown here. This type of vibration, each type of vibration corresponds to a Raman peak. What analyzing in Raman spectrum? First, position. The peak position, which is related to the vibrational energy of corresponding mode. The width relates to the structural disorder or excited state phonon lifetime. The relative intensity is related to the cross-section for inelastic light scattering for each mode. Advantages is a non-destructive technique. We can use the sample again. We can use very small samples, few microns, probes solids, liquids, and gases, probe matter under extreme conditions, temperature and pressure, is easy to combine with other techniques, X-ray diffraction, nuclear magnetic resonance, computational simulations, thermal techniques, etc. Limitations. Theoretical prediction of a Raman spectrum is impossible because we need to know the wave functions. And from the quantum point of view, this is impossible to describe the wave function. Very difficult to use in conductors. And difficult to observe due to screening of the Raman signal if there is luminescence. And also thermal radiation when we are working at high temperatures. Okay, thank you for attention. Now, in sequence, Dr. Rafaela.
So, can you hear me well? I will be presenting today some of Raman spectroscopy applied to glass. And I'm sorry, the configuration is not quite good, but I'd like to bring this general history of Raman. And what I think very interesting are the things I have left highlighted in orange. So we have the prediction of Raman and its discovery on the 1920s. And we got quite right. Do we have the light? Oh, whoops. Sorry. And we have just after the first Raman spectrum of a glass being recorded. And then we got really good advance in terms of instrumentation. We got Raman grating, the first lasers, and then the CCD. And on 1980s, we were able already to record Raman spectra under extreme thermodynamic conditions. And that's what I'm presenting to you this morning. So when we talk about extreme thermodynamic conditions, we're talking about temperature and pressure. And these are quite different. So if we get to understand that in terms of a potential well, we have the temperature will just increase the energy to get to surpass things that occur with an energy barrier. Whereas when we're working with pressure, what we get is the change of the potential itself. And that occurs because we're bringing matter on a different equilibrium position. And people usually ask me, why do we get to study extreme thermodynamic conditions? And the first reasoning is to describe glass and melt structures in harsh environments. And with that, we get to assess the center of Earth or even other planets. So these conditions right here are ideally those we can somehow get in the laboratory in terms of pressure and temperature, not the Raman, but like general in synchrotrons and so on and so forth. And yeah, we get to analyze a lot of things. And when we're working with Raman more specifically, we can work on harsh environments, for example, on Mars surface. So right now, when we are talking, we have a rover walking on Mars and collecting samples and taking Raman spectra. And another important thing in terms of principles is when we study extreme thermodynamic conditions, we get the knowledge on phase transformation and also the involved mechanisms. So during this week, you hear a lot, I think, ex situ and in situ, and I'm just explaining what it is, just to make sure everybody's at the same page. So when we get ex situ, we put a condition of pressure temperature, but we release it and do our measurements after that condition is taken. Whereas when we do in situ things, we are measuring exactly at that condition of temperature and pressure. And if you are not convinced so far, one of the most important reasons for applications is getting to optimize and tuning resulting properties. So we have the glass under specific treatments. We will get the glass ceramics, which is a topic on Friday, I think. Or ultimately, you can get to understand and try to optimize one of the highest limitations of glass, which is the fracture. So high pressure. Pressure is force over an area. For getting high pressure, either we need to put a very, very big force or work with a very, very low areas. And usually what people do is decreasing the area. So we will always have a compromise in between pressure and area. And for that, also the volume of the sample, which is being investigated. So here are the two most common. We have the DAC, which is a diamond anvil cell, which is quite nice for studying in situ if we're working with light and also X-rays. And the problem is we get into micrometric samples, but you get to assess very extreme thermodynamic conditions. Otherwise, we can work with press, which are millimetric samples, but we get into intermediate conditions. I'm just explaining the DAC because I think it's quite interesting. So we have a diamond. We put over a diamond a gasket, which is a plate. This plate is drilled. Inside the hole, we put our sample. We put a ruby, which is a pressure calibrant, and we put the pressure transmitting medium, which usually is methanol-ethanol. Just for you guys to have an idea, this is the size of a DAC. And this is the size of the gasket. So inside a 100 micrometers diameter hole, we need to put all of that without losing anything for getting a good experiment. And then we can assess it as well with high temperature with a microfurnace. This time we haven't brought them, but I have heard that you guys are going to IFSC this afternoon. If you want to see the Raman lab and also this device, we can arrange a visit right there, but you should talk to me because the lab is small. And then I come into glass structure, and this is the best analogy I could find in between a glass and a crystal. So we have as motifs the books, and we have on the shelf these books are organized, which is a crystal. And then on the desk, they are not well organized, and somehow that's the glass structure. Let's do it more scientifically. So I'm using here Zakharyan model. It was designed in 1932. And right here, you guys see the original draws of Zakharyan. And these are TN imaging that were done in 2012. And you can see how beautiful it is. So sometimes we need to go beyond Zakharyan model, structurally speaking, but it gets to cover a lot of important things that we get to understand glass structure. So I'm being simplest, but for good reasons. For understanding the glass structure, we have that as we get further of an atom of reference, it starts getting more and more disordered. But when we get very close, we have really well-defined polyhedra with coordinations numbers, bonding distance, and bond angles. And according to Zakharyan model, this polyhedra gets connected by the corners with different intertetrahedral angle. As we get further and further, we have the connection between this tetrahedra and different degrees of connection, which are the polyhedral connectivity, the QNs. Since they are very important in this morning, I will spend some time on them. So, according to Zakharyan model as well, we have the network formers, which are oxides that are able to form polyhedra with low coordination, which connect by corners. And if we add elements like alkali and alkaline earth, it will get into other polymerizations. So just getting like vitrosilica, it's a Q4. As we start adding more and more alkali and alkaline earth, we start progressively decreasing the connectivity with Q3, Q2, and a distribution of this, guys. So what's the Q that you will hear a lot this morning? It comes from a quaternary tetrahedron, so Q, and N is the number of bridging oxygens. What's a bridging oxygen? is the oxygen that connects a tetrahedron to the other, or more generally, network former towards another network former right here. And then what's an NBO, non-bridging oxygen? It doesn't do the bridge in between them. So it's a terminal oxygen in the network, but that's the point. It's not terminal because it's there alone. It will have a modifier connected to it. And in terms of vibration, what we get is that if we take, for simplicity, the simple harmonic oscillator, we have that frequency is equal to the square root of the spring constant divided by the mass. And as we get to increase the QNs, as we get to increase the connectivity of our network, we get to increase the characteristic frequency of vibration of these QNs. So generally, the Q4s have higher frequency of vibration than Q3, than Q2, then Q1, and then Q0. And in Raman spectra, these are showed especially in this region in between for 800 to 1,200 in tetrahedron in silicates. So just for you to have an idea how complicated it is to do the curve of it, we have the exact same composition here, which is PbSeO3. And then right here, it's a glass. And right here is a monoclinic crystal. So for monoclinic crystal, we can just measure, sometimes go to low temperature, and we get to see which band is in which place. For doing that with glass, we'll have the following section, which will be very, very interesting. And along with a curve, so sometimes we can do a curve fit, which is very nice because we get into a description that is, let's say, complete, but sometimes we don't get to do the curve fit somehow. And in these situations, or maybe when we need to see if we are doing the curve fit right and data is really telling us that it's going towards one direction, it's very important to do the barycenter. So I'm just explaining it here with the QN units, but it could be in other bands. For doing the barycenter, we take the band. So the barycenter is the geometrical mean that reflects the simultaneous evolution of the envelope shape and the shift of the peak maxima. And to take it, which will be just one parameter, we get to integrate the band we're interested on. And just to make sure, if we take the derivative of that integral, we'll end up with the same sign outside of a constant. And then we normalize that integral, and we take the exact wave number where we get 0.5, the barycenter. And then I'm showing right now some interesting results using this barycenter as a function of pressure and temperature, first starting situ and then going in situ. So the first one is a function of maximum pressure on densified soda lime silicate glass, and the barycenter of the intermediate Raman region was very powerful to get into a calibrant of the maximum pressure. And then we were able to do that with lead metasilicate. And right here we have the barycenter. And right here we have experiments done with Brillouin spectroscopy. Brillouin spectroscopy gets to analyze matter as a continuum. So like that, we get somehow connected to elastic constants, and we get into, for example, elastic and saturation limits as we put pressure on it. So which is that? Elastic limit would say we put pressure, we release it, and we'll return to the same configuration as before. Whereas saturations limits, you put pressure, you remove, you put more pressure, you remove, you end up with pretty much the same thing as a prior pressure. And that's very nice because some Brillouin equipments are not very spread, and we got to do the same analysis with elastic limit and saturation limits using the barycenter of Raman spectra. And this same Raman spectra were curved and gave an idea of the QN distribution as a function of maximum pressure. So we can combine them or can use either of them, depends on what we would like to do. And now I'm showing some in situ data. So I like this picture a lot. It's of soda lime silicate as a function of pressure. And the reason I like it is because in last school, 1 year ago, it was into one of the posters. So last year in the poster, this year is in the presentation. They have done the very same thing using as well the intermediate range, intermediate frequency. And this is very nice as well. This, like, we showed compression, we showed the compressions, and we could curve fit all of it. But what I like about this result is, let's take a very same pressure, and we take the barycenter. We see that in a compression, the compression cycle, we get into an hysteresis, and we just show it by doing a barycenter, and I think that's very powerful. And right here, we did the barycenter, and we are combining altogether experiment and simulation for getting to the QN distribution as a function of pressure. And now I'm going towards temperature. And the barycenter has shown to be very interesting to get into phase transformation. So this is the barycenter of the QN region. And these are how the temperature gradients, temperature coefficients change as a function of the phase we're analyzing. So we have one for glass, one in the supercooled liquid, one in the crystal, and we get that we would change the inclination, the slope right here, and from that we would get a TG that can be somehow obtained by Raman spectroscopy. And another thing we got here, which I think is very interesting, is when we put temperature to analyze spectra, sometimes just in a run, we see small changes that it gets into lower and lower frequencies, and these changes are very comparable to the changes that we see on crystals. And it could be not to a change on the QNs itself, but due to a change on the anharmonicity, which means our idea of describing vibration just by taking the simple harmonic oscillator is simplest because we need to take the other terms that are higher. And then I'm showing you once more. That's interesting for seeing phase transformation. In this work, we have seen the formation of metastable phase at different temperatures, and it's one metastable phase at 825 K, another distinct metastable phase at 875 K. And when we got to analyze data, we could see very distinctly the regions of supercooled liquid, and then supercooled liquid and metastable phase, which is different in each one. And then the start of formation of the stable phase through the end of the stable phase at the very end. And this one I'm not showing the barycenter, but I think it's a very powerful thing of combining Raman and DSC, because from that we get to understand some of the SSC crystallization peaks and which phase is formed at each point. Oops. So the examples I have presented here are not restrictive at all. And I think, or I hope you could get that Raman spectroscopy along with extreme thermodynamic conditions can provide valuable information to the glass and glass ceramics communities. And I would like to emphasize that glass can get into very complex structures. And in my personal point of view, the best way to analyze it is as an elephant study. So the analogy is like putting blind people seeing an elephant. And if each of them get to see a different part of the elephant, they will say that the elephant is just that part. And you guys are going to see in this school a lot of different methods. And the beauty of science, especially when we're dealing with complex materials, is combining all of it together. Yeah, so I hope you guys got to understand and like a little bit of all of it. And thank you so much for your attention.
Thank you, Rafaela. I have some questions, but I'll give opportunity for the students to get a nice T-shirt. Questions, please? Yes. Could you please, again, spell your name, and so you get to memorize your name and the institution, and then a question.
So thank you for your lecture. I'm Adam from Warsaw University of Technology, Poland, and my question would be, because you mentioned that this barycenter change is related to the unharmonicity. Is that the property of the bonds in the glass, or of the, because like traditionally Raman scattering is related to phonons, but of course we don't have phonons in glass, and how would you say is the relation between the vibrations and the scattering? Because it's like, is it like unharmonicity of a single bond or something like this?
Yeah, the definition of phonon for glass is quite complicated. So people right there are very... phonon sometimes is a definition when, especially when we get to work on the reciprocal space. And when we are dealing with glass, we get like an infinite, it's disordered. So for getting a unitary cell, you would get all of that. And when we get into the reciprocal space, what you get actually is, that could be whatever, if you know what I mean. And then be careful of calling phonon. Yeah, but using the barycenter, we have used it for studying crystals. And we have seen good trends as well. And we're trying to apply it to other systems, and so far it's working.
It's important to remember the phonon dispersion relation, the picture. Phonon is the optical phonon where the Raman scattering probes is near the Brilliant zone center. That is, in K around 0, the propagation of vibration is very, very large. If you break the periodicity, in less, the vibrations are localized. So we cannot call the vibrations by phonons. Okay?
I don't know. I'm not the physicist. So I'm going to talk about the barycenter part of your question. When I was doing my PhD, I didn't believe anything that I saw in the Raman literature, and everybody was saying something different. Okay? So I was very confused for quite a number of years about what people were showing and who to trust and which study to look at. Because I didn't believe anything I was doing with the curve fitting that I'm about to show you in the next presentation, I did everything with a barycenter, and you saw one or two examples there. The reason I think this barycenter is so incredibly powerful, you can use it on any section of your spectra where you see changes. And the barycenter, I have yet to see a study where somebody has used the barycenter, sees a change in the barycenter rate of deflection as a function of temperature, pressure, composition, etc., that doesn't exactly correlate with the other things that are happening in the system. So it's non-biased. Who cares about the interpretation? You're seeing a change where you see the change. And Rafaela showed excellent examples of where you see the change related to TG, where you see the change related to crystallization, where you see the change related to different compression mechanisms as a function of pressure. So it's a non-biased check that everything you're doing in, let's say, a more nuanced analysis of the spectra is actually changing where you see it's changing. The interpretation might be refined through time, but at least you're showing the change, and that your fit or your other analysis has this unbiased check to it. So it reinforces that.
On the barycenter then, I would basically agree with you, but the baseline can influence the barycenter a lot. So you have to work out some procedure to always use the same baseline, or how do you deal with that question?
The question by Professor Eckert was, well, the baseline affects the barycenter a lot. Assuming that you have a similar enough baseline, the major changes are still going to be the major changes. The absolute deflection of the barycenter as a function of, again, pressure, temperature, or composition will change. The rate of change will change, but where you see massive changes in the behavior of the barycenter doesn't. So it's actually not so strong unless you're manipulating your baseline every single spectra with that same temperature, pressure, composition series. So it's less, I'm not so concerned about that, actually. If you're doing a fair and honest baseline, that's relatively consistent.
Well, okay. Continuing on this discussion on the barycenter, could you show again one of your slides on a soda lime silica glass? A model soda lime, 1, 2, 3 soda lime silica glass. Yeah, this one. Okay. The centroid is moving with pressure, right? But then what? What's going on with the glass structure? Okay, the centroid is moving, but I want to know what's going on there. What's changing in the glass structure?
Yeah, that's the thing. Sometimes I don't agree with some authors because some of them use the torpor relationship, which was derived for vitreous silica, and they try to extend it towards some silicates. And then we get into some correlation in between the frequency and the angle of aperture of like SE angles.
So you're saying that the angles are changing in the glass structure?
Yeah,
What's
some
changing?
authors get to correlate this change of the barycenter in terms of change of the angle. You put pressure, you put a lot of pressure on it. Like, just for getting an idea, we've got the entire Eiffel Tower over a coin. We have 20 GPa, and they are working with 20 GPa. And what they're showing is this band changes, and these authors are correlating with Thorpe equation, and yeah, sometimes we discuss how fair it is just to extend it.
Maybe to add a little detail. So you have to know what frequency range they're looking at and what they've said about that frequency range before you've done that. So in this case, the Berry Center is around 665 there to start. So these are the bending modes, and that's why Rafael is saying that the bending modes will change frequency as a function of the intertetrahedral angle for the glass. And in this case, which is, I didn't participate in this study, I haven't read it, but they're seeing no change in the rate of angle closure up to 20 GPa, which to be honest is a little surprising from what I know. But again, I have no details of that.
Thorpe equation, which was idealized for vitreous silicate, so we need to make sure all the assumptions are really being followed. Sorry.
Yeah. No, I understand. I understand it. Thank you. Thank you. Any other question? One here, another one there. Okay. Oops.
No.
So in fact, I have two questions. You use this wave number, the Raman shift, the center position. Which vibration it come from?
Yeah, so the general interpretation is that this is from silicon, oxygen, silicon,
Yeah.
and you have a bending
Binding
mode,
strand.
bending in the plane of the SiO-Si.
Okay, but why is the bandwidth increased with the pressure? The bandwidth increased with the pressure.
When you see an increase in Raman spectroscopy, somehow you get into an increase of disorder. So maybe you're getting to a higher distribution with a higher number of different things. That would be my first guess. I don't remember his result. I just thought it interesting because it was in the previous poster, and I brought it. Sorry.
Okay. Yeah. Thank you. In fact, I have one more question, if I may. When we use Raman technique, we have different wavelengths, excitation wavelengths or pumping wavelengths. What kind of principle we should follow when we choose the pumping wavelengths for Raman measurement itself?
Which wavelengths you use?
Laser source, different laser source.
So
what kind of principle?
in theory, when you're using Raman, it's like Professor Pisani has showed, you excite your material, and then you remove the original light. So in terms we get just Raman phenomena occurring, you would pretty much get the same result no matter what's occurring. But what we have occurring in the lab is that sometimes we have the luminescence, and we need to choose a wavelength that we will not kill or we will not hide our Raman results with the luminescence. Or for example, when we are working with high temperature, we have the problem of Planck radiation. And in this case, it's always good to work further from the red. So blue or in this direction. Yeah.
Okay, I think. Okay, thank you.
There's no just as a vague general rule, more inorganic, you can go a little bit higher energy because it boosts your intensity.
Okay.
If you have more organic, you tend to go lower energy so you don't burn your samples and destroy them during the measurement.
Okay,
but it really depends on the material. I've seen everything, almost everything used for almost everything. So.
Yeah, because when I measure some unknown sample, I have to try several times to compare results from different exciting sources, then choose the best one. What I want to say is, if there is an easier way to find.
Yeah, so if there's absolutely nothing changing and all is first order Raman, there's no fluorescence, no sample damage, if nothing else is changing, when you measure a Raman spectra with a blue laser, a green laser, or a red laser, the spectra are identical.
Okay.
Now that you asked that, I should show a slide where I will show this exactly for a crystalline sample where everything is identical for all 3 wavelengths. It should not matter, but with the caveat of if there's no fluorescence and everything is first order Raman.
Okay, okay.
No resonance, no fluorescence, no damage.
Okay, okay, thank you. I get.
Thank you for the presentation. So I have just simple question that when the broadening is happening and also this centroid position is increasing, so what it has impact on properties and what kind of properties of glass are dependent on or it affect what it affects on such properties. So that's simple.
We have seen it in situ at very high pressure. So the properties would be at very high pressure. Sometimes when we return to low pressure, and that's sad, we can have some densification, but some of the structure of the high pressure will no longer exist at low pressure. But yeah, we get to see changes like in general, densification can change mechanical properties, refractive index, and we were talking, Ricardo, about relaxation times, and so a lot of physics and a lot of properties by inference.
Do you have the example of Brewon and Raman?
Yeah, I do.
So here's a nice example. So Brewon spectroscopy probes the acoustic modes in your sample. And there's geometries, not the experimental data that's shown, but there's geometries where you can get the longitudinal and transverse acoustic modes. From those sound wave frequency speeds, you can calculate the moduli of the material. Okay, so if we were able to do that here and we didn't have just one node, there's only one mode due to the geometry of this experiment and due to the selection rules of Brewon. But the barycenter changes here at the elastic limit and the saturation point will correlate with changes in moduli of that material. And so this is a nice, fast way. The Raman spectra, the experiment on the left took a day. The Brewon on the right took multiple days and can only be done in half a dozen labs around the world. The measurement on the left can be done in dozens and dozens of labs around the world in a fraction of the time. So it's a way to see where, to test where to expect property changes and then to understand them so you can reverse engineer those properties in a much faster, more efficient, and easier way that's much more accessible to most people worldwide.
Okay, thank you very much. I think we can go on now with Benjamin.
Okay, before I get going, I want to go a little deeper into how to quantify Raman spectra, and specifically I'll be talking a fair bit about curve fitting. I didn't mention yesterday, but most of my early work is on silicates, but I've now started into borates, and I'm currently starting a project on phosphates and tungstates. So I have a bit of experience with these materials, but by far and away, the majority of the work I've done is with silicates. One of the most common things you'll see with papers is curve fitting of the Raman spectra to try to extract some more nuanced information. Everybody here just saw the discussion, and we kind of hedge, oh, what's it from? Where's the origin? How do I tell the meaning of that? Okay, you see the changes in the shifts in the peak, but what do I make of it? So one of the key aspects and one of the things that correlates to a lot of property changes is the polymerization of the network and its connectivity. So I'm going to be talking about how to take a spectra and actually extract quantitative information so we can quantify that polymerization and tie that to the properties. I'm not going to show much property data. I'm going to stick to actually how we treat the spectra. You'll recall from Professor Pisani's introduction, each spectra will have a peak and we can describe a few parameters of that peak. For instance, its height, its intensity, its width, or its frequency. I'm going to talk about how you break down the spectra. Why do we curve fit? And another name for curve fit is decomposition. So why do we do this in the first place? Because I think sometimes I read some papers and they've forgotten the point of why they're trying to curve fit in the first place, which is to extract some more nuanced information. I want to go back in, with a little bit of history here, because I think there was some very influential early work that was largely mistaken, and it led us down some very not productive pathways. Then I'm going to switch to some crystal works. You saw the picture from Rafaela of the glass and the crystal. I've very much, and I showed that yesterday in my introduction, I've very much done all my studies where we compare isochemical crystals in glass, because I think there's a lot of nuance where we can add a lot of detail that is very certain in the crystal, but much less certain when we start to talk about the structure of the glasses. So I'm going to start with the crystals, and I'm going to use those to define some physically reasonable limits on curve fitting. Okay? Everything I do is based on a deep understanding of the physics of where these Raman bands come from and how they, what information they can tell us about the material, again, specifically with an emphasis on the polymerization. We'll then transfer that to glasses and how they compare to these crystals, and I'll wrap up with some final thoughts. So I'd like to show this study under the title of What is the Goal of Curve Fitting? This is a study by Poon, Putness, and Saleh back in 1990. And if you like Raman, this is a very beautiful study. And they look at this crystal structure. It's a magnesium aluminosilicate called cordiorite, and it's high temperature polymorph indiolite, where you have some ordering phenomenon. Here, the silica and aluminum sites are separated. Here, the silica and aluminum are randomly distributed in a ring. And they see some very interesting effects. A clear split with at least 2 peaks that becomes broad into a gigantic hump. And it's difficult to say exactly what and where the changes are here. And so these authors decided to do a curve fit. And they put these 3 peaks under the curve, and they related them to both the ordering of the aluminum and the silicon tetrahedra, and to the different phases from orthorhombic to a modulated structure to a high temperature polymorph that's hexagonal. And they use these to, the parameters from these peaks to look at the order parameters associated with the phase transition, and they said, oh look, we very faithfully reproduce this phase transition, the details of which, go read the paper, it's very nice. That was in 1990. Then this group in Austria, Kandel et al., they came back in 2011, a couple decades later, and they did a DFT calculation of these crystal structures. And they nailed down each of these vibrations, what the difference between what was experimentally measured and what was calculated in their first principles simulation, and they attributed it to very specific different sites within the crystal. Now I show this example because Kandel actually shows that there's 4 peaks calculated instead of 3, so there's probably a couple extra underneath this one. On one hand, you could say, well, Poon was wrong, and Kandel got it right, and he refined the interpretation. On the other hand, the analysis of Poon still faithfully reproduces the phase transitions. And so it's an excellent example where Raman can very quickly follow and determine the phase transitions. What's the goal of curve fitting? It is to resolve these peaks so that they can be parameterized and associated with a physical process that's ongoing in your material, and to therefore use that quantification to actually reveal something more deep about the effect that's going on. Kandel showed that this does not mean that you have to have the perfect answer, but you have to have a pretty good answer, okay? You don't have to be perfect here. The goal is not to absolutely believe every peak that you put under there, but it is to faithfully track some process to better understand it. This means when you have a curve fit and you have values to go with that curve fit in terms of the position and the width and how the frequency changes, it means that the result can be tested, and it also means that those model parameters can be transferred to other systems. So it's really important that the results of curve fitting are meant to be used by other people. Okay? That means you need to have enough detail for other people to reproduce it, which sometimes means putting a lot more detail than is often found in some papers where people are publishing. Just one note on the terminology here. We can see that the peak in the example of Poon was decomposed into 3 separate little peaks there. Okay? That's curve fitting or decomposition. They mean the same thing. This is often confused in the literature with deconvolution, and deconvolution involves a product of 2 functions where there's 2 influences on the peak. This is very common, and I'll speak about this briefly, in where you have multiple sources of broadening on peaks that change these line shapes. So don't call it don't call it deconvolution. Call it decomposition or curve fitting, folks. Why do we need to do this? Beyond the fact that we want to quantify processes and changes in the structure and correlate them with changes in the properties, we have this problem in glasses. So this is a series of barium silicate. Glasses are obviously the broad spectra. Crystals are obviously the sharp spectra. This is a Q0 crystal, a Q2 crystal, a Q3 crystal, actually a crystal with both Q2 and Q3 here, and another pure Q3 crystal. And you see that in comparison to the glasses, we have very broad features. And so it's difficult to tie down and say, oh, this one peak here is changing when you have such a broad spectra. So this is where curve fitting actually enters, because we need to break down these very broad signals and see how things are actually changing. And if we don't actually break it down in detail, we won't be able to correlate that with other properties. So let's go back in time and look at the origins of this. And I show these examples to start because I want to emphasize my points a moment ago where the parameters that you're looking at should be able to be tested and transferable to other systems. And in the rest of this talk, I'm going to show you why these examples are particularly bad examples and some that you find in the literature. On this side, there's so many peaks here with so many parameters, you could come to almost any model solution and you're not going to have any resolution or sensitivity to anything's going on. There's too many things moving at once. Okay, so this type of fit is even if it's correct, it's not very practical. And you can imagine that if you transfer this to, any of you who have done some Raman on glasses, transferring this to any other system is basically impossible. On the other hand, this is a much more common example over here. And the major problem, which I hope to convince you of today, is that these very large peaks that don't correspond to the peaks in the spectra are governing the properties of these other peaks. And so if you say, for example, this is a band associated not with a QN, but something else, and you just report the Q3, Q2, or Q2, Q3, and Q4 bands, this is actually governing the properties of the fit found in the QN bands. And so if you haven't done a lot of good detail to characterize that middle band, it's influencing what's happening on other sides. So you can produce the changes that you want to produce if you know how to manipulate the spectra. And I'm not suggesting authors are doing that. I'm suggesting it's a byproduct of letting fits just without some physical basis for them. Oops. So this is the famous study, curve fitting of Raman spectra, by Björn Meesen from the Carnegie Institute in Washington, D.C. It was published in 1982. And this is a very nice example of where a lot of the AI goes wrong. This publication itself has somewhere around 450 citations. And if you search curve fitting of Raman spectra, you're probably going to see this publication because it's the most commonly cited ever. So let's take a look at it because I think this kicked it off back in the early 80s. First thing they said in this study was line shapes and the quality of fits are determined by statistics alone. Okay? They made no assumptions about what the peaks and what the vibrations in the glasses look like. Then they said when we do the fitting, the intensity, the width, the position are all treated simultaneously as unconstrained variables. Okay, they said everything's independent, we have no idea about anything, let's just let everything loose and see what the statistics dictate. Then they said the number of lines are determined by getting a really good fit. We want to minimize the residuals. And when we minimize the residuals, we have a really good fit, and then we can stop adding more peaks. The last thing they said is when the residuals show a nice random distribution, the fit's good. Okay? For the rest of my talk, I'm going to show you how this is wrong, that we should not determine the quality of fits by blind statistics. The peak positions in terms of the QN species that Raffaello was showing have well-constrained intensity, or at least widths and positions. The quality of the fit is not going to be strongly determined by minimizing the residuals in all actuality. Oftentimes we need a few extra peaks to minimize not to minimize the residuals, but to obtain a physically meaningful fit. The last thing, your residuals should be random. I agree with that. So this has really influenced a lot of people, and you see it cited until today, so I'm not bringing this up because it's not relevant anymore. People still use this method. This is some of the results they show about a decade later from the same group. Again, they stuck with this. We don't know why line shapes are, but they did show this, and they said, okay, here's the reduced chi-square, how well a fit it is, and they said, look, when we use these Lorentzian line shapes, the fit's really bad. There's a really high chi-squared. When we use Gaussians, on the other hand, this goes way down and becomes really tiny. And the conclusion from that is that everybody used Gaussian line shapes for the next 3 decades. Okay? The next thing they show, or at least that I want to emphasize here, these residuals are highly non-random. You have a big residuals in the middle, and if you compare that to the residuals down here, this is fairly reasonably random. This is quite non-random, and so that's the difference there. About a decade ago, in 2012, again, the same lead author here, he said, okay, we don't know what's going on. We attribute the things after the fact, a posteriori. Okay, so they made post-interpretation attributions to justify their interpretations. And I hope to convince you that we can say a little bit more on the front end that leads to a more physically reasonable interpretation in the talk ahead. If you're unfamiliar with Raman spectroscopy, I just wanted to start with, oh, the title's really long. What should the line shape be of a Raman peak? If it's a first order Raman, no other effects, what should it be? If there's no other influence on the lifetime of the photon, and as you just heard, there's no phonons in glass, so that's a mistake there, but vibrations, let's call them. The excited state, the peak will have some width here that's inversely proportional to the lifetime. And this is called phonon damping, and it has a Lorentzian line shape, and it's basically a form of the Heisenberg uncertainty principle. As the lifetime gets really long, your energy, how tight you can fix that peak position, goes to 0, meaning that you know very confidently where that peak is, and it has 0 width. So we should start as a first order. First order Raman modes should have a Lorentzian profile. Okay? This is very important because, like I said, lots of people in the glass community use Gaussians, not Lorentzians, because of that work back in the 80s. There are different contributions to the line shape. First of all, we have temperature and pressure broadening. As you increase the temperature, increase the pressure, to answer your Professor Zhang's question, you get a Lorentzian broadening of the line shape. And if it is, again, first order, no other effects, increasing temperature pressure, this Lorentzian line will just become broader naturally due to those effects. On the other hand, we can have some Gaussian component. We can have this broader line shape here. This can be due to the Doppler effect or to the chemical environment, including disorder. So in glasses, we know we have some disorder, so maybe some peaks do have some Gaussian components, but it should, but we'll look at whether that's true or not and how much that affects things. The final factor in Raman spectroscopy, everybody who's got a Raman spectrometer, if you're familiar, each of the different major companies do things in a different way. Okay, there's different experimental contributions, and you also have some, you can get some power saturation effects from having too much energy on your sample. These can have some combination of Gaussian and Lorentzian line shapes. Yes, Lauren, go for it. If your measurement was, so in this case, it's not really a big effect in Raman, but if your measurement was on a similar time scale to that vibrating, you could have a one signal as the vibration moves away, and one as it's coming towards the detector. Is again common in spectroscopy, but not so common in Raman because the signal's so weak. You got to remember that only one, as Professor Pisani said, only 1 in a million actually interacts with these vibrations in the material. For those of you who are a little more sane and less inclined to line shapes, I just want to compare directly. If we keep those main parameters of the peak absolutely constant, and we just look at what a Gaussian versus a Lorentzian means, the Lorentzian has these big tails that extend quite a bit further than the Gaussian. Here, the Gaussian signal basically before you get to 2 steps away from the center goes to 0, where even at 4 steps away from the center, you still have some minor contribution from the Lorentzian. So just to compare for those of you not so familiar with these line shapes. There's many ways to mix these line shapes together, and in fact the profile is often some degree of a mixture. That the way we describe the mixture most commonly is the Vaught curve or pseudo-Vaught. I'm not going to spend much time on it, but you can get mixtures between these end tails where the tails, as you have more Lorentzian component, you have bigger tails. As you have more Gaussian components, these tails disappear. And if we kept the area constant, not the intensity, this means that a Gaussian peak will have a higher intensity locally than the than a more line shape, sorry, with a more Lorentzian component to the Vaught curve. I want to point out this study. It's too bad the title is not there, but Alameda and Santos back in 2015, they're the only study that actually addressed any sort of fitting issues in Raman spectroscopy. So I give them a lot of kudos for that because it's a difficult topic that a lot of people have some very strong debates at. So I like their study. I like what they have to say, even if I don't agree with it all. These are a couple bad fits. You can see that on the left-hand cap, there's gaps in the spectra. You can see that the baseline is quite a bit off here. On the right hand, you again have this gigantic curve in the middle of the envelope that doesn't necessarily correlate with the main peak. The main peak is on this 979 curve. So how your assumptions that go into this peak here really strongly influence what's happening to the peak parameters of the rest of the spectra. When you compare that, so these were on the left-hand side, whoops. On the left-hand side, these are Gaussian. On the right-hand side, these are also Gaussian fits, but comparing 3 versus 4 peaks under the spectrum. If we switch over to our Lorentzian profiles on the left and our pseudo-Vaught curves on the right, you can see that the fits get better, and the major peak is where the major peak in the spectra is. Okay, that's really important. The major peak should always be where the major peak is. It shouldn't be this guy on the side here. So these are pretty good. Nonetheless, we still have quite a bit of overlap. You see the tails of each peak influence the other peaks on the extremes. So this makes the parameterization of that codependent. It's not independent of the process. So we want to deal with that a little bit better. So just to summarize, basically from a decade ago and before, they assumed that all the parameters were independent. Okay, the number and the shape of the peaks was often determined just by the statistics of the fit. Oftentimes, this led to very large peaks with a lot of overlap where the fit parameters are going to have a high degree of covariance. What that means, if we go back to the first slide of why we do our curve fitting to make things testable and transferable, it means that these fits are often non-transferable, highly codependent, and even depending on the assumptions that go into the fit. And that's really difficult. If you want to do good science, you want it to be testable and transferable. So we're not being effective scientists by having by entering these types of problems into our research. Let's move to crystals. I want to show you a few examples just to prove so everybody's clear, because this was never shown to me, and I wish somebody had shown me at the beginning, because it clarified really what the starting point is for understanding what's happening in the glasses by knowing absolutely what's happening in the crystals. So this is a very nice study I did. We looked at a couple crystals, including sandbornite, or BS2. And Eduardo Gomes, who's now in Belgium, he was in Spain at the time. He's a Brazilian that is a quantum chemist who does DFT calculations. He and his supervisor were nice enough to simulate the Raman spectra of these two phases, and we looked at this as a function of temperature. Here's a fit of, so the next couple slides I'm going to show you this fit. They have the main spectra with the main peak here. This is focused in on that Q3 stretching mode. You have the residuals down here in the gold, and I'm going to show you a lot of zoom-ins of this small part of the spectra down here so you can really get the details. When we do this fit, and we fit each of these with a pure Lorentzian, we get a center of 1075 and a width of 4.6, and it really nicely reproduces the spectra. I hope you'll agree with me. If we do the same exercise with now Gaussian peaks, we also, it's the exact same spectra, but just changing the line shape here, we get also another very good peak with some higher residuals right around the peak center is very normal. This is equally good. So just to compare those with Lorentzian and Gaussian, 1075, 1075.1, 4.6, 4.6. Okay, Professor Moulton, you're jerking me around. You just told me Lorentzians is everything, Gaussians are bad, and now you're saying Gaussians and Lorentzians are the same. Okay, guys, just bear with me. If we go up to 800 degrees Celsius and look at the components, the parameters of the peaks are still very similar. However, when you look at the fit of the spectra, there's no way that this Gaussian peak actually reproduces a peak. At higher temperatures, Gaussians fail to reproduce that thermal broadening that is natural to a first-order Raman scattering mode. Okay? I could show you a whole series of these up to 1200 degrees Celsius. I can show you all of them. They all fit with Lorentzians, and as soon as you increase the temperature, Gaussians no longer fit. Okay? That's the point here. Gaussian line shapes do not reproduce first-order Raman modes and crystals. Most crystals, most of the first-order Raman modes, all the first-order Raman modes with no other effects, have a Lorentzian line shapes. We go a little bit farther, and just to put the nail in the coffin, at 1100 degrees, we still have a very good fit. The residuals start to get a little less random, but still, this is much better than the Gaussian fit for the same temperature. So, Raman peaks, first-order Raman peaks, are Lorentzian in shape for crystals. But in glasses, we know we have disorder. So let's look at this. Well, first, before we go to glasses and look at the effects of that disorder, let's look at what the reasonable limits are for the parameters, these widths and positions and so on. When I started as a PhD, about a decade ago, these were the two most prominent publications by Macmillan and Neuville, 1984, 2014, and they showed this. As a function of the Raman shift, you have different QN modes associated with different polymerization. Here's 100% silica, here's 33% silica, and the main stretching modes decrease in their Raman shift as a function of that composition. Here, you are hopefully familiar, as we add modifier oxide, you get different QN species that Rafaela showed in her talk. And at the top, he put this frequency, with some numbers here and then bars. Okay, so I don't know about you, but my first question is, what about the gaps? What about the gaps in here? How do I deal with these gaps? I have no idea. Do Q-through modes also occur way up here at high frequency or not? I didn't know, I wasn't sure. So I spent some time at CERTEV in the Department of Physics over at UFSC as a part of CERTEV, and I looked at about 160 crystals, some of which are duplicates, let's say 150 independent studies, and I just looked at crystals with only a single type of connectivity, only a single type of QN mode, and I just calculated a simple mean and standard deviation for each of the QN species, and I got these values right here. This is published in a study from 2022, an American mineralogist, because it turns out geologists really like all of these crystals. What I showed was that here's the Q3 range, here's the Q2 range, here's the Q1 range, here's the Q0 range. Q4 has a little question around it, because remember, it's bound to everything on either side, and this prevents it from moving very strongly, and therefore it has quite a low Raman intensity relative to the other QN species. So those were mean frequencies with some standard deviation. You can go out a couple standard deviations, and you know you're capturing mainly one type of stretching mode from one type of connectivity in your glass. The other interesting thing about this barium silicates, you know, these crystals have obviously been studied for decades and decades. But what got me really, what caught my attention about the barium silicates is that they have these compositions. The composition here, by the way, is in the oxygen to silicon ratio. They have these crystal phases by the blue and the green that have mixtures of both Q2 and Q3 species. One thing I forgot to mention when I showed that glass, everybody is familiar that all glasses have a number of QN species. They have a range, a distribution of connectivities. This is very, very rare in crystals. And so because these crystals had this distribution and they had a ratio of 1 Q2 to 2 Q3s, 1 Q2 to 3 Q3s, and 1 Q2 to 4 Q3s, I thought, oh, this is a perfect opportunity to go in and identify a vibration associated with those species when they're connected to something that is not itself. Another way to say that is they're heteroconnected when you have Q2 connected to Q3. With my friends in Spain there that did the DFT calculations, they simulated the spectra and reproduced the frequencies of all the modes, and then they told me the physical origin. They said, these atoms are involved in this vibration, and so I could tie my spectra and the frequency of the modes to specific arrangements associated with different polymerizations in these crystals, where it was easy to calculate. What I got was this result here. As this is the Q2 crystal with only Q2 in the red circle here. This is the Q3 crystal with only Q3 there for the barium silicate, barium disilicate, barium metasilicate. And these green dots were different, changing the ratio of the proportion of Q2 and Q3. So when you have a lot of Q3, you shift the Q2 stretching frequency to quite a bit lower frequency, down here, close to 920 if I remember correctly. The Q3 has much less of an influence, okay? It's surrounded by 3 silicate tetrahedra anyway, and so the influence is quite a bit smaller, and therefore these vibrations lie within the natural distribution of Q3s anyway. But these Q2s were quite heavily quite strongly influenced and shifted by almost 50 wave numbers below here. I said, okay, that's great. These barium silicates are wonderful crystals, but maybe they're weird and maybe I got it wrong. So I scoured the literature for other crystals that show this mixed connectivity, okay? I came up with some, not surprisingly, alkaline earth silicates, calcium magnesium silicates, and I plotted them up too, and lo and behold, they fill out this line. There's a nice consistent behavior and down shift to lower Raman shift of the Q3 modes as you depolymerize the system. And you get the inverse trend where there's a shift to higher frequency for the Q2 as a result of depolymerization towards the ideal frequency of a sample with only one type of connectivity. Okay, so this is I think this is a really important result because when we deal with glasses, we're constantly dealing with this distribution of connectivities, and we want to relate that to the polymerization. And this effect, to my knowledge, this is the only study actually showing the effect of heteroconnectivity and having some distribution of these species in the glass. Okay, so that's the frequency. We fixed frequencies. We have some statistically robust limits on where we find different QN stretching modes. Whoops, wrong way. How about the width of the peaks? This is a study from my PhD supervisor, and some of his buddies, Wayne Nesbitt and Grant Henderson. They looked at Q0 species and the width of the peaks in the crystals. And they looked at these isolated tetrahedra, Q0, in silicates. We have magnesium orthosilicate. We have some phosphates here, lithium orthophosphate, strontium and barium orthophosphate, and lithium sulfate. All crystal structures where there is known to be a single isolated tetrahedron. They measured the width of these peaks, and you see they range at room temperature. This is in temperature Kelvin. At room temperature, they range up to close to 10. Let's call it 13 wave numbers, okay? For all of them. They then went on and looked at the temperature effect for these Q2, now not only Q0, but also Q2, and this is plotted slightly different. This is the difference between the width at room temperature and their width at high temperature. So they looked at how much those widths increase as a function of temperature for Q0 and Q2 crystals. What they found is for all of these tetrahedra, the stretching mode increased basically the exact same way when you compare apples to apples, right? So they're starting width to their high temperature width. They also showed that for about 1,000-degree increase in temperature, you get, on the order of 20 to 25 inverse centimeters width increase for all of these species. So all of the tetrahedral species are acting in a similar way, and their widths are behaving in a very limited range of values. That at high temperature, 1600 K, here is somewhere around 25 to 30, and can be a little bit more if we go to higher temperature. So there's some systematics to the width here. The last parameter is the intensity. The ROM intensity you actually measure is a function of a bunch of parameters associated with the laser and the thermal population of the vibrations to begin with, and the density of states over here, G of nu. There's this other parameter in here, the coupling, the light to vibration coupling constant, and this is generally not known. So it's very difficult, and as Professor Pisani said, it's almost impossible to calculate. And when we don't know the structure, and we don't have a model already, unless you're a person who does simulations and then you have all the information, it's very difficult to know how the light couples to these vibrations to actually quantify the number and proportion of these species. So you usually need another technique. And if you look in all my studies, thanks to Professor Eckert and some other professors in Germany, I've done the NMR with the Raman to show the effects and compare and contrast these. For those of you a little more familiar with NMR, I've done all this for NMR, and you can see the effects on that. Just to let you know that simulations are improving. It is almost impossible, but not completely impossible, to reproduce the intensities of crystals. This is an example from an Italian group, Stangaroni et al. From 2017, so 5 years ago. The relative intensity, so this is the measured spectra on the bottom, this is the simulated spectra on the top from first principles. They get quite a good agreement in the relative intensities, except for at the low frequency zone. And the reason I point this out is to show that the theory is developing. There are people working on this for crystals, it works. For glasses, still very much impossible. But the reason I also want to show this is because at low frequency there are some disagreements. So the picture here at low frequency is quite a bit more complex than at high frequency, and that's why I focused on the stretching modes, because the stretching modes have a much better reproducibility between the simulations and the actual measured spectra at the current state of things. So let's move forward to look at some glasses and liquids and see how these compare. This is another study by my supervisor. It's definitely not the first time this idea has been put forth. There's been many authors, including Neuville, including Macmillan, and many others. But it's a recent example, and it's a little more clearly stated than perhaps was done in the past. In this plot, you have the Raman shift on the y-axis, the mole percent of the modifier oxide on the bottom axis. And you can see this trend as we saw for the crystals. You have highly polymerized crystals up here, lowly polymerized crystals up here, and these pluses sit basically, these are the main position in the glasses, for the peaks in the glasses. They sit basically within the same frequency range, okay? This is a well-known result. It's been known for many, many years. There are many studies that actually follow crystals and have in situ Raman that go into the melt phase, as Rafaela showed some examples earlier, and we see no dramatic change in terms of the major frequency where the most intense peaks are upon melting. One of the other things you see in the literature, and that has been used to be a justification for this broad peak in the middle, this is a spectra of pure SiO2, and you see these little modes down here. They're very weak in the Q4, again, because it's stuck there. It's held in all directions. It can't vibrate very strongly, creating a strong polarizability to give us our intensity. When you add just 5 mol% sodium oxide, you get a massive increase in the intensity of this feature here, and you get some shoulders on either side. Because this shoulder matches that in silica, it is generally assumed that this peak, this is a blow up of that section, so you can see just how massively increased the intensity is upon the addition of 5% sodium, where you're breaking up that network and producing MBOs. This shoulder is always or almost always assumed to be associated with a change in the polarizability of the Q4 species that are attached to the Q3 species. That's resulting from the breakup of the network. If you look on the other side, though, in silica, there's a T2 mode that's been attributed. If this T2 mode here, it doesn't produce a similar strong shoulder. And so some people use this T2 to represent that gigantic band in the middle that they say is there. But when you look at this, in my opinion and current understanding, there's no increase in the polarizability of this mode. And in fact, the attachment of Q3 probably perturbs it so that it doesn't exist anymore. So I just want to show you that because you'll see the T2 mode in there, or a silica bridging oxygen mode. That's the justification for those bands. I'm not convinced that it's a very strong justification. Let's look at some more complicated glasses. This is a figure I showed earlier. Here we have 28 mol% barium at the top in the glass, these crystals that you've seen. And here we have almost a metasilicate 45% barium. We get 3 broad humps. If you look at the, now remember I said that this is the Q2 peak. When it's connected to a Q3 peak, it's been downshifted. And this is the crystal with only Q2. So if you look at the limits of these, this major peak is very well constrained just to be a product of Q2. And when you decrease the polymerization, when you add modifier oxide, you get this shoulder that builds up on the low frequency side that's still probably associated to a similar effect of the Q2 with Q3, where it decreases in frequency, but the Q2 itself also decreases in frequency. Let's look at their widths in the alkali metasilicates here. When you compare the crystals on the bottom, this is a study from Bancroft in 2018. This is a similar situation to what I showed earlier. The width of the peak for sodium, lithium, and calcium metasilicates. The glasses at room temperature seem to have a similar frequency to the crystals at high temperature. Where you make that cutoff is somewhat arbitrary, obviously, but glasses always seem to have this more or less 30 wave number increase in their width relative to the corresponding crystal. And you'll note that their temperature behaviors are very much parallel here for these crystals shown. So glasses seem to have a width of the crystal in the molten state, in the liquid state. Okay, so this is where we get our fundamental limit in the width of the vibration in a glass. And there's certainly more work to be done proving this for more systems, and certainly for the phosphates and some of the other tetrahedral systems. But the assumption is that this is true for all of the stretching modes, for all of the QN species. So we have a lower limit, and at room temperature, our widths should be somewhere quite low, and I give a little bit more room, 40 wave numbers, plus or minus a bit. I would say less than 50 is usually pretty good. I'm not going to go, I've got about 20 minutes left, I want some room for discussion. To actually go into the details of the process of fitting is a whole other discussion and involves lots of iteration and took me many months to come up with the model that I came up with for the barium silicates. So you have to be diligent. But some things to consider. This is the barium silicates from disilicate, or just 28% barium. This is the 45%, and you can see that there's a nice shift in the spectra, and every time as you depolymerize the system, you get a big shoulder on the low frequency side of these peaks. So some general points to consider is that we assume that there's not drastic changes in the polarizability. If there's drastic changes in the polarizability of one or two of these species, everything I'm saying needs a whole revision, one step over. But for limited composition range, where dramatic transformations are not generally thought to be happening, polarizability is assumed to be constant, so that we can convert the areas under these curves when they're curve fit into concentrations. You have to remember that it's a constant sum. You always sum to 100% QN. Professor Eckert brought up the point about the baselines. Where you cut on this is not going to be consistent if you have another peak coming in here. So there's a lot of room to play with the baseline underneath here. I generally pick the minimum on the high side. You can see immediately, and if I extended the spectra, there's another contribution here that's coming in, and so you want to pick the minimum. So know that there is a little bit of wiggle room depending on where you set those limits, and it's sometimes difficult to set the limits absolutely equal and comparable all the time. What I can say that if you have a nice set of spectra where the baseline is systematically shifting, you can usually do a pretty good job, and this introduces a minor uncertainty into your fit. And for example, in this case, I had a fit where I have a whole new peak coming in around 38% of barium added. And so I knew that there's a massive change when you have this peak starting to grow. That's going to be true independent of the baseline, okay? Then always I recommend to students before they start, just look at the spectra and see what you see. What I mentioned about the peak positions and the shift to lower frequency, take a look and sort of take some time with the spectra before you're trying to start fit. The fit is always going to produce great numbers, and everybody's comfortable with numbers because they have fixed values and they're very good. But take a look at what the spectra is telling you and where those maxima are shifting as a function of temperature. It is also useful, and Raphael showed some nice examples, to use a suite of samples that are one sample as a function of pressure or temperature or time. You also is very helpful to show, like the example I just showed, where you have a change in the composition. So having some series where you compare changes, even if they're not absolute, they will definitely be relative, and the barycenter will show where massive changes are happening. That'll be revealed in a suite like this. So taking one spectra alone is a bad idea. Taking 6 or 10, great idea. The peak intensities should follow the envelope. So here's my ultimate fit for that 45% barium. The major peaks correspond to the major peaks, right? Here. And we have some shoulders that require 2 additional peaks to be put in on the low frequency side. The major peaks follow the major peaks. The major peaks of your fit follow the major peaks in the spectral envelope. This is really important. This should always be the case, unless you have a very strong and convincing argument otherwise. You should always try to use the minimum number of peaks. People like to put more peaks because it improves their fit, but this often just introduces much larger uncertainties and should generally be avoided. Use the minimum number of peaks as possible. Always report, have a table of those main peak parameters in your spectra so that other people can use them. This is meant to be used by other people, so you need to include that information, whether in the supplemental or in the main article. I recommend the main article, but sometimes articles get big, so supplemental is totally fine. Always, always, always include the raw data in the supplemental files. Again, we stand on our science, but we hope it gets better with time. And maybe in the future, one of you will come back and say, look, Professor Moulton, I redid your stuff. I reanalyzed your spectra in a different way, and I've got the answer now. And I'll say, great for you guys. But have that raw data so that other people can use it, independent of your fit. And then remember, your fits should be testable and transferable. You want other people to use them. You want to gain a better understanding of the structure, and as a consequence of the structure, what the property changes are in your material. So I will leave it here, but take high quality spectra. There's a few final points to go away, sorry. You see how these tails start to become important, okay? You need good signal to noise. I see a lot of spectra taken with low diffraction gratings that are very noisy, and you can fit any type of peak in there. If you want your model to be testable, you should have a good spectra. This question of heteroconnectivity and a distribution of QN species in the glasses, for me, remains very much an open question. It's not been looked at for the more depolymerized species, despite the fact that there's some very interesting rare earth crystals that show connectivities, structures with Q0, Q1, and Q2 in the same structure. So this needs more refinement and is an area for further development. I hope I've convinced you that we have some good physical parameters as a starting point for our fits, and we shouldn't be having massive peaks with 100+ wave number within our spectra. And I've given you some values here. I'm happy to share this presentation if anybody wants it, or any of the examples I've showed, so you don't have to remember all this off the bat. Just come chat with me. Happy to share. These limits are, for the physical parameters, just to review, we have very well-defined frequency range for the major stretching motions. Their widths are generally less than 50 inverse centimeters, okay? And then you have to do the constant sum to get the whole distribution of the KM species. And finally, as you've seen, do some systematics with crystals and the glasses of isochemical compositions. Do a series with pressure, temperature, time to compare how those spectra evolve. And again, I will hammer this forever. You want to do this so that other people can test your results, so that other people can use your results. So make it testable and transferable. Muito obrigado. Thank you very much. I hope you all learned something.
Thank you very much for your excellent lecture. That's why I became impressed with his presentation several years ago in Buffalo when you were a student.
Thank you.
Very good. Great. Questions? Colin.
Yeah, thanks so much, Ben. Thank you, Edgar. Thank you so much, Ben. I want to push you a little bit, though, because when you quantify the Q species, you're still reliant on the NMR to calculate the effective cross-section. So to be able to quantify your Q units, you still have to use NMR and rely on NMR to get the cross-section. So is there a future you see in Raman where we're not reliant, that we could quantify without having to go to a more expensive technique?
100%. So I know that you haven't looked at this in fine detail, but you have thought about it quite a bit. And I know that for the alkali silicates, those cross-sections are known, okay? So we have those as a basis on which to build more advanced models. This process, I am very optimistic, should go quite quickly. We have tons of data. There's tons of Raman spectra out there where we can start to build off these cross-sections, starting with the alkali silicates and then adding a third component. The spectra are there. We just need to reanalyze it and see where the problems are and refine this. So I see a future very not so far away where the cross-sections are known for a lot more compositional range and to be more broadly applicable to all the wonderful glasses that you guys are studying. So I think it's not so far away.
I'm sorry, how do we go from where we are today with much data in the literature, with not so many quantified precisely, where we are today, to a future where, you know, Sarah can pick up a Raman spectra and draw quantitative Q speciation or ring speciation?
I have a wonderful challenge for you, Professor Wilkinson, my dear friend Colin. You're the machine learning AI guy. Come on, batch processing. I'm the experimental guy. Professor Eckert.
Yes. Yes, thank you so much for this truly amazing lecture. Many of these issues on peak fitting also affect NMR spectra. And just to respond to the comment there, oftentimes it's actually, you need both, you know, NMR and Raman to interpret and assign NMR spectra. It's really also good to look at the Raman. The questions that I have is two of them. One of them is in the end the conclusion to generally do a Gaussian decomposition the correct thing to do it in glasses? Is this, and when I looked at the last picture, it seemed pretty, these peaks seem to be pretty Gaussian that you decomposed there, no? Yeah. Or do you still have to use some sort of a Voigt function to kind of adjust the Gauss-Lorentz contribution and so on? So that's my first question. The second question, one advantage we do have in NMR is that we can do different experiments and piece together the information by using the complementarity of two different experiments. In Raman, it seems more limited, although you have this possibility of running polarized spectra. And this, you didn't show any of this here, but what do you see as a prospect of maybe addressing the points that he made by adding the polarized spectra and jointly interpreting both in the future?
Great, thank you, Professor Eckert, and really thank you. Let me start with the second question first. And of course, now that I said that, it went out of my mind. What was the second question, sorry? Polarized Raman. Okay, there's a lot of polarized Raman spectra out there. It turns out there's, you need very specific situations or types of vibrations to really use that usefully. Professor Doris Monk has done some very nice polarized Raman on titanium silicates and shown that there are some modes associated with titanium tetrahedra that are quite quite polarized in their ratio. Besides those cases, all of the polarized Raman, so I've done actually polarized Raman on the barium silicate glasses, one example which is shown now. They generally show where the major peak is quite depolarized, and in between you get some polarization. Lots of people have tried it. I haven't seen much useful information. It doesn't mean it's not there. I just think there's a lot of other issues about the overlap and how many peaks that are much more significant and influence how you interpret the spectra than whether something is completely polarized or depolarized in terms of its vibration. So it's a lot of extra work, and only in some specific cases is there really a strong advantage to distinguishing vibrations. Not to say it's not useful, it's just you have to take twice as many spectra, it takes twice as much time, and takes a whole other layer of processing. So yeah, that's the reality of the situation. I'd just like to, so let me answer your question about the peak shapes. Depending on exactly the function you use, so the pseudo-Voigt function I showed earlier is actually the function that I used to fit these. The Lorentzian component of these two peaks that I've attributed to the Q3 species is about 65%. So there's 65% Lorentzian and 35% Gaussian. As you go down to Q2 and Q1, the Gaussian component increases. That, in the Q1 case, that could be because of, oh my gosh, this could be where the baseline is cut here. So these have been offset a bit, so it's a little more clear to see. They've been downshifted. It's not that the fit's that bad. So in general, when you look at where the QN frequency ranges are, the ranges get compressed as you become more depolymerized, and more importantly, the separation in the ranges becomes smaller. From what I can tell, but this is completely anecdotal, and as far as I know, nobody's ever said this in the literature, but the more depolymerized you get, the more Gaussian component in your line shape there will be, okay? And this seems to be a function of that disorder in the local environment and how many nearest neighbor, other nearest neighbors there are. I just want to shout out, just because NMR is brought up, I have a beautiful example, educational example, and a shout out to Professor Eckert here. This is a figure I sadly didn't put in the paper. And I really wish I had, though all the data's in the paper, but I hadn't put this in the paper. So on the left is that glasses that I've been showing for the last 45 minutes. Oy. Okay, and you see this peak is new at 37% barium added. And before that, I just get these two features here. And then afterwards, I get a third feature here. This is the silica mass NMR spectra. And you can see, anybody who's done silica NMR with alkaline earths present know that there's no resolution of the peaks. You don't see any resolution of the three peaks. So Raman is really essential to go with the NMR to solve this problem and understand what's going on. The important observation is there's always on the high field side of the NMR, low field side of the NMR, there's a constant shift in the envelope. But on the other side here, there is almost no shift until we get to this green spectra. Then it starts to move to lower chemical shifts, or to more positive chemical shifts. So the correlation of this new Raman peak with a change in the shift of the envelope told me, very importantly, when to put a third peak in the silica NMR spectra. And that was only possible collaboration with NMR people. Gotta love them.
So yeah, this is a very good example where we need a complementarity. But to save the honor of NMR here, I would like to mention that we also did static NMR, and with static NMR, you can actually quantify very nicely the Q4 component. And once you know how much you have of that, it helps with the deconvolution of the magic angle spinning spectra.
Yeah. This study had two types of NMR, static, magic spinning angle, and Raman, and only with all three techniques could I actually quantify the result. So I am quite confident, if I speak confidently about this work, is because I'm quite confident it agrees with all the NMR, and there's only one solution for all the spectra, okay? So you really got to use every tool in your toolkit to come to the very robust answer.
Very good. One last question before the break.
Yes, thank you. Thank you very much for very, very informative lecture. So I have just two simple questions. You told us about baseline, that how to choose and background.
I told you nothing about baselines.
Just little you gave one comment. But what about that one you chose the major peak, so you can see it, you can see the position, but how would you choose other peaks which are not majors? How you would choose, for example, if you give us an example and maybe first graph in the first one. I mean the position.
So the position.
Second.
So, you know, for, this is now the barium disilicate spectra, and this is that Q4 peak, that high shoulder that I showed.
Yes.
This is the peak, because of the inflection here, you need at least one more peak.
Yes.
Some people say two. I just put one, and I fixed all the parameters because I said these are both, remember my range of Q3 is limited. So I took the range and I said everything in this range is a Q3. So these are both Q3 peaks, and I fixed their parameters except for the relative intensities. And the fit gave me the relative intensities to match the envelope.
And when you refine it, you free it. You make it free. When you refine the position, so you...
No, I never fixed the position. I only fixed the width and let it vary to fill in the space that the statistics actually dictate.
I see. You just guess the position, and then after that you refine it, and it's...
Yeah, I mean, all the programs you can put peaks where you want, and then you do some sort of minimization of the residuals.
Thank you. And also, if there is anisotropy in the peak, how would you deal? For example, if it's leaning towards right direction or to the left, so anisotropy, for example, is...
Yeah.
So how would you deal fitting in that case?
Right now, I wouldn't, and I haven't. But if these things have asymmetry, it's a whole other set of problems.
I see. Thank you.
Yeah, sorry, I haven't thought about that deeply.
I'm watching what time is it now?
No, just
please.
Very briefly, very short.
Okay.
One
Very good.
suggestion to make, we sometimes do in NMR and also EPR, we actually, regarding the baseline, because the baseline is also always in NMR and EPR also an issue. So we make the first derivative of the spectrum, and the spectrum itself, and then we'll fit both the spectrum itself and the first derivative. And if you get the same results, then you have a good idea about the baseline.
Absolutely. I totally agree and endorse that comment. Good, thank you very much. One more. Sorry, Josiah. Go ahead, Josiah.
It's just the instrumentation question. So I was just wondering, in your opinion, do you think it's a good practice to change, for example, your collection parameters for like samples in the same series, like changing your power, your exposure time, number of scans? So for example, you can add samples in a specific series. Is it a good practice to change your parameters, or do you just keep it in order to get good signal, right? So do you change your parameters, or do you just keep them pretty constant every time you move?
Yes. Keep everything constant.
Okay.
So you do your most difficult samples, your extremes, and you see what parameters work, optimize them on the extremes, and then pick some value that works for everything or that approximates for everything, and then apply that consistently. You don't want to change the experimental parameters. You don't want to change anything in the optics. You just want to change the sample, measure, same conditions.
Right.
With high temperature, sometimes you really lose the signal, so you do have to collect more iterations, more repetitions to get better statistics. But that's usually by that point, you've already lost a lot of information anyway, and it's not so critical.
Okay, thank you.
So keep things the same.
All right.
Thank you so much to all speakers. It was a real good opening for the school. I have a few announcements before the coffee break. Just out of curiosity, I was in Kolkata in January, and that's where Raman discovered the effect, for which he was awarded the Nobel Prize in 1930, using a shoebox, you know, not a $500,000 equipment like you have, Pisani. It was a shoebox, very nice. I visited his lab, actually, with Anna. We had a picture there, and it was incredible. So this is, you have to visit that lab, his lab. Anyway, few announcements. The bus will leave, says Laurie, my boss, at 1:40 from the hotel. So please be back after lunch to the hotel and bring your snacks then in the bus. So at 1:40. And then I have 6 people registered, officially registered for credit. I want to see them here to make sure that they're attending the classes, and we'll meet, say, here before the break if you are attending this lecture. And then I think, the posters, you know, had a disaster with the posters. There's some wind last night, some posters disappeared, but Ricardo was able to collect all of them, and we'll bring stronger tape on Thursday, you know, really stronger double face tape on Wednesday, but you have collected most of them anyway. So, thank you very much, and enjoy your coffee break. Edu, então você take care, né? Eu vou lá pro Lamave.
A Ana Thaís, acho que ela...
Não, mas não, amanhã ela share outra e tal. A gente divide.
Pode deixar.
Você share isso aí.
10 e 15.
10 e 15, é. O duro é trazer o pessoal de volta, cara. Isso aí é um inferno, trazer o pessoal de volta. Os posters fora. Deixa eu ver quem são vocês. Quero ver vocês. Aqui.
Okay, I think we must start. Yes, and after this nice coffee break, welcome all of you back, and I have pleasure to start again the section with Professor Hackett and talking us about NMR. Okay.
Yes, thank you very much for the kind introduction and the opportunity to contribute to this school. What I want to show you is what electron paramagnetic resonance, or sometimes called electron spin resonance, can do to learn about glasses. And for this, we need to first introduce a few fundamental principles, the spin concept, the so-called Zeeman interactions of the magnetic moments of the electron with the magnetic field, and the interactions, the hyperfine interactions, particularly with atomic nuclei, that influence the spectra, and then what we can learn from it. EPR spectroscopy is a technique that is under active development, and besides the standard experiment, which I'll be talking mostly about in this school here, is called a continuous wave EPR, in which you basically apply microwaves with a sample in the magnetic field continuously. That's what is called continuous wave EPR, and you record the response of the sample. Aside from this, there are advanced pulsed techniques, which I will mention, and I'll show some applications. And also lately, the combination of EPR spectroscopy with NMR spectroscopy is a very powerful new line of research, which yet has to be applied to the glassy state. So this will be a perspective for the future. I want to, at this point today, just give you a little bit of a phenomenology of EPR, because it's not a technique that is applied widely to glasses. But I want to show you the potential, and I want to particularly acknowledge also the contribution of Claudio Magnon, who's in the lecture, who's in the room, who is also a member of CERTEF, who taught me EPR when I came as a professor in NMR spectroscopy to São Carlos. And of course, I would appreciate Claudio if he responds to some of the questions I cannot answer at the end of the lecture. Anyways, so EPR spectroscopy. We are dealing here with a spectroscopy of unpaired electrons. So you need an open shell atom, an open shell particle to get the effect, to observe the effect in the first place. An unpaired electron that has a magnetic moment, and the magnetic moment is interacting with the magnetic field, and this is called the Zeeman interaction over here. Here's the Zeeman Hamiltonian linking the energy with the angular momentum operator representing the electronic spin. And essentially, it is not only the spin magnetic moment that affects the spectrum, but there's also oftentimes a contribution of the orbital angular momentum of the electron, and the combination of both of them dominates the response, and that is contained in this factor G here, the so-called Lande factor, which for a pure spin contribution would be 2.0. Yeah? But it deviates from this when there are orbital angular momentum contributions. And it's these orbital angular momentum contributions that make the Hamiltonian anisotropic, yeah, directional dependent, which complicates the spectra on one place, but on the other hand will be a source of information. Because anisotropic interactions imply information about distances, about orbitals, about wave functions. Okay. So basically, with regard to experimental aspects, how to record an EPR spectrum, there's two ways. In standard electron paramagnetic resonance, you are exposing the sample continuously to microwaves. So typically, the so-called X-band spectrometer has a microwave frequency of 9.5 gigahertz, yeah? And the sample is positioned in a magnetic field. And you're continuously changing the magnetic field. It's called the so-called field sweep. Yeah? And when the Zeeman energy is comparable to the, or equal to the electromagnetic energy of the microwaves, then you get a change in the magnetic susceptibility, in the magnetic properties of the sample, and that is being recorded, detected in the EPR detector, so basically recorded as an electromagnetic response, and then you get a signal. So this is the classical way of doing EPR, and much of what I'm talking about will be about this. In NMR spectroscopy, this method started out, Markus will talk about nuclear magnetic resonance after my talk. It started out in the same way, but it soon turned into a different technique in which the magnetic field is not swept, but is actually kept fixed. And instead of using a continuous wave irradiation, one uses the polychromatic aspects of pulsed excitation. Yeah? So the NMR spectroscopy is done in a pulsed mode, exposing a sample in the magnetic field, and then recording its response to pulsed excitation in the time domain and using the Fourier transform principle. Now this method now is also, during the last 20 years or 30 years, 20 to 30 years, has is being applied in electron paramagnetic resonance as well. So we have both techniques, each one with advantages and disadvantages, but they are complementary. Okay, so here for the classical EPR in a continuous wave mode, the experimental setup, you can see here the sample is within the cavity, which is basically the probe in which this it's being exposed to the microwaves, while in the inside in the homogeneous spot of a magnetic external magnetic field. Okay, and then the magnetic field is being swept, yeah, linearly varied, and when you go through a resonance, then you record an imbalance here in this microwave bridge, and you get a signal. Just a little detail about the methodology is that you actually record not the signal itself, but the first derivative of the signal with regard to the magnetic field. And this is done by modulating the sweep on top, also with a sinusoidal variation of a magnetic field. So this method of field modulation brings you, automatically records the first derivative of the spectrum, and that has advantages with noise reduction and also an increase in resolution, so it can aid fitting. Anyway, so there are basically three types of EPR spectrometers available out there. The X-band is operating at a magnetic field of 0.35 Tesla and 9.5 gigahertz. That's a classical method. I think more than 50% of all EPR spectra nowadays are still recorded in this way. Then there's a Q band, which is a 4 times higher magnetic field. And then there's a W band, which uses a superconducting magnet and operates here at 95 gigahertz. The W band spectra are almost exclusively recorded in the pulsed mode, so in the new pulse Fourier transform mode. And there's a variety of other bands, but these are the most common ones. Yeah? We call them bands because it's a microwave frequency that is not monochromatic, but the frequency can be changed a little bit in the during the process of their creation by the microwave source. Okay. I mentioned before, we have to deal, when we're measuring and analyzing EPR spectrum, we have to deal with the fact that the Zeeman interaction is an anisotropic quantity. Yeah? So basically, the Zeeman interaction means the interaction of the electron with a magnetic field. If it were pure spin, it would be isotropic, because spin doesn't have any directional dependence. But because there is always a contribution from orbital angular momentum is connected to special wave functions that have a specific directional dependence, you get this anisotropic contribution. Yeah? And this has as a consequence the fact that the spectrum and the resonance frequency, so where you observe the signal, at which frequency exactly, will depend on how the sample, a crystal, is oriented in the magnetic field. If you put a single crystal into a magnetic field and you change its orientation, you will change the resonance frequency. That's called anisotropy. And in a polycrystalline material, as well as in a glass, you don't have a specific orientation. You have a statistical distribution of orientations of a special axis defining the interaction with respect to the magnetic field. And the orientational statistics give you, in many cases, a line shape like this. So you have basically this asymmetric line shape, and it has to do with the fact that the parallel orientation is much less probable than the perpendicular orientation. Possibilities. So it's for this reason that the perpendicular orientation here is much stronger in intensity than the parallel orientation over here. It depends basically on the sign of the orientational angle. But one thing that is good about EPR and also NMR is the fact that it is truly quantitative. We don't have to worry about scattering cross-section like we do in Raman spectroscopy. We do not have to worry about oscillator strengths as we have to worry about in optical spectroscopy. NMR and EPR are quantitative. If two signals are of equal intensity, they represent two species of equal concentration. Anyway, getting back to the line shape of EPR spectra in general, so what we see, what we expect are line shapes like this, yeah? And in the first derivative, they turn into this over here. Yeah? You can see that the advantages of recording the first derivative. Yeah. I should mention that a line shape like this is only observed if we have still a local environment of the interaction that has some residual symmetry, namely the so-called axial symmetry, which is typically characterized by the presence of a threefold or fourfold axis of rotation, yeah, or sixfold. So that means that we only need to differentiate between the orientation parallel and perpendicular. Perpendicular. The parallel orientation then is normally using the Cartesian component z, and x and y are the perpendicular, and in this case, for axial symmetry, x and y are equivalent. They're the same. If you have a lower degree of symmetry, one calls it rhombic symmetry, then the interaction in x and y direction may not be the same. And in this case, the theoretical line shape will look like this. Then you have three singularities here, or inflection points that you can characterize. In the first derivative, it looks like this. And then again, what these spectra allow you to do is to characterize the parallel and perpendicular component, or the z, x, and y components of the interactions separately, directly. You can read it off directly from the spectrum. Okay. So this is the first part. We remind ourselves again, the interaction of the spin, the electron, unpaired electron, with the magnetic field is anisotropic, and in the description, theoretical description, we then treat the G, which is a constant for an isotropic situation, now like a tensor. Yeah? It is described like a second-rank tensor with the principal components gx, gy, and gz. In addition, there's a second type of interaction, and that is the following. The electron spin interacts with the nuclei that are on the same atom that are carrying the unpaired electron, the same atom that are carrying the unpaired electron, or nuclei that are on an atom to which the unpaired electron atom is bonded by a sigma bond. Yeah? In both cases, the spin state in which the nuclei exists, shown here in green, yeah, will influence the resonance frequency of the unpaired electron. So we actually see, instead of one signal, we see two signals depending on what spin state the nucleus is in. And the interaction is basically what's called the Fermi contact interaction, and the strength is given by the hyperfine coupling constant A. Yeah? So the Hamiltonian is very simple. It's simply the scalar product of the electron spin operator with the nuclear spin operator, and A is a constant. In the case, we have an isotropic situation. If in the solid state, however, and then we could simply count number of peaks. But in a solid state, an additional complication is that this A here, the hyperfine coupling, is also a tensor. That is, we again have a directional dependence on this. Yeah? So this complicates the interpretation of EPR spectra on top of the G anisotropy. So it's shown over here. Yeah? The hyperfine interaction is anisotropic as well. So in the end, when we want to simulate a spectrum, analyze an EPR spectrum, we have 6 parameters to specify: gx, gy, and gz for the G tensor, and ax, ay, and az for the hyperfine tensor. So we actually require 6 parameters. Actually, it is worse. It is even worse because the 2 tensors defining the G, defining the Zeeman interaction and the hyperfine interaction not necessarily are coincident. So in addition, one needs to consider that there are 3 angles defining how these relative coordinate systems are oriented relative to each other. So you actually have 9 fitting parameters. And there's a 10th one, the one that the same problem that Ben had been dealing with. We need a line broadening effect and a line shape, an idea what the line shape is. Yeah? So in the end, it's a 10-fit parameter. And then this already, when you have a poorly resolved spectrum, becomes, and this is for one species. No? When you have a spectrum, it's a considerable challenge to arrive at a sensible fit and at an unambiguous fit. And I would like to advertise for the people who developed this, the program EasySpin, which is freeware, and can accomplish this sort of feat. I'll show you a few results now. What can you do? So fitting 10 parameters. Well, what can you do to narrow down the number of parameters to get a sensible answer from the spectrum? Well, for one thing, you can record the spectrum at 2 different magnetic fields, or 3, or 4, because the Zeeman interaction is field dependent, and it increases in strength of the magnetic field. The hyperfine coupling is field independent and remains constant. So for a simple molecule like this is a so-called tempo radical, which is simply a typical Drosophila for a simple unpaired electron spin. You can see how the line shapes change at different magnetic fields. These are simulations. So when you then are able to fit with the same set of parameters all 5 spectra, then you have confidence that your parameters are correct and you haven't landed in a false minimum of your fitting process. Yeah. Okay, what else can you do? You can do pulsed excitation, which I'll mention later, which gives you independent information about the hyperfine coupling constant. And you can use the power of computational chemistry. DFT can make very good prediction about the 3 angles defining the relative orientations of the G tensor and the A tensor. And with all of this, we managed we managed reasonably well to analyze an EPR spectra of molecules and crystalline materials. More challenges arise when you're dealing with transition metals and rare earth ions. And of course, these are the ones that are most interesting to glass scientists because you incorporate these rare earths. Yeah, if you have them available and you can afford them. In Brazil, they're quite expensive, but we, of course, know of their utility in the development of optical sensors, biosensors, exploiting the fluorescence of rare earth ions. The fluorescence characteristics of rare earth ions are very important for the application of high-tech glasses. And of course, they are influenced by the electronic environments of these rare earth ions. And EPR is just a perfect method to study this in a fundamental way. Yeah. The same goes about transition metals. Yeah. In this case, we have oftentimes not just one unpaired electron on the atom, but we have several. We have multiple electron systems. In the case of manganese 2+, it's 5 of them. So we have a spin 5-half system. Yeah, in the rare earths, it's at times even more complicated because it's not the spin itself, but rather the combination of spin and orbital angular momentum that combine to a total angular momentum J, and the J can go up to 11/2. Yeah, and then basically, yeah, we have, because of these higher spin quantum numbers, additional effects like zero field splitting due to intra-atomic inter-electronic interactions and ligand field effects. Again, magnetic hyperfine couplings with nuclear spins are important in influencing the EPR spectra of transition metal and rare earth ions. In the case of these species, the G anisotropy can be huge, and we may not be able to use traditional continuous wave EPR spectroscopy anymore. We then actually require the pulsed EPR techniques. Yeah, oftentimes we have broadening effects due to relaxation, which I mentioned, which forces us to slow down relaxation by going to 4.2 Kelvin. So a good EPR spectrometer is always equipped with a cryostat where you can measure at liquid helium temperature. It may be necessary to do this. In the case of rare earth ions, it is generally necessary to do that. Yeah? So here is a little brief summary, yeah, of what species you can easily study with EPR in glasses. There's a so-called Kramers rule, and that is the following. The number of unpaired electrons in the atom has to be odd. So either 1, that is spin 1/2, or 3, it's spin 3/2, 5, it's spin 5/2, and so on. But if the number of unpaired electrons is even, let's say, for instance, like a species of vanadium 3+, it's a D2 ion, the EPR spectrum is generally not observable. With rare exceptions, you cannot observe non-Kramers ions by EPR spectroscopy. Yeah? So this is out of the question. That has to do with the intra-atomic, inter-electronic interaction between these electrons, causing the zero field splitting. Okay. Now, so anyway, so it's these candidates which basically the EPR spectroscopy narrows down to, and of course many of them have important role in glass science and engineering. Okay, I want to give an example, copper. Now copper is relatively simple, you would think, because it has only one unpaired d electron, so it's a spin 1/2 species. So many of these complications with zero field splittings do not arise. Nevertheless, you can see here, this is a very simple glass actually. It's a frozen solution that is present in the glassy state. It's copper nitrate in DMSO. You chill it down and you get a glass. And here you see the EPR spectrum of the copper 2+ ion, showing a beautiful line shape from which we can get the G anisotropy and also the hyperfine coupling. There's 2 nuclei on copper 60 nuclear isotopes in copper that have a magnetic moment. namely copper 63 and copper 65. And the interaction of the unpaired electrons with the copper 63 and copper 65 cause the nuclear hyperfine splittings. Now from the shape here, you can see that we have axial symmetry. So we have this typical line shape, except now that in the parallel component here, we don't see one peak, but 4 peaks, and this is because of the hyperfine interaction. So basically, you can look at it like this. This is the parallel component interacting with the isotopolog nuclear 63 copper in the +3 Siemens state. This is with the in a 1/2 Siemens state, in the -1/2 Siemens state, and the -3 half Siemens state. Yeah. Now you would expect to observe this also over here in the perpendicular component, but as it turns out, because the interaction is very anisotropic, the A perpendicular is very small and is actually not resolved in the spectrum. Here we have the special case and situation in which the two coordinate systems of the A tensor and the G tensor are coincident. So it's a very simple example. If they were not coincident, the same simulated spectra would look like this. So here we have the coincident, and if there is an angle, just the main angle between the principal axes called beta over here, deviates from 0, we see what happens in the simulations. Spectra are then becoming much more complicated. I'd like to thank Claudia for actually doing the simulations for me so I could present this here. Okay, but back to our simple frozen glass here, frozen solution from which we can extract this information. So what do we get out of it, and what do we learn now about the local structure of copper on this? Well, one thing immediately clear is we have a local environment that is axially symmetric. That means it has this special symmetry of a rotational axis, 3-fold or 4-fold. In fact, that is the one that predicted by the so-called Jahn-Teller effect. Yeah? For an octahedral copper, we actually do not expect perfect octahedral symmetry, but rather a distortion that can lower the energy of the complex. And if the distortion is tetragonal, for instance, over here, we have this situation here, that the surrounding of a copper is not octahedral, but rather tetragonal with 4 short distances and 2 longer distances. Yeah? Yeah. So this is one way the system can respond to the Jahn-Teller effect and lower its local symmetry and lower its energy in this way, because now you can see that the highest orbital here in energy is only singly occupied, yeah? Whereas the one whose energy is lowered is doubly occupied. So this structure has a lower energy than the perfect octahedral structure. And that's basically what Jahn-Teller said. Whenever there is a chance to lower the symmetry due to distortion, it will happen. Yeah? So very simple. That's why no copper, there exists no perfectly octahedral copper environments. The same situation in the case of titanium 3+, only there the distortion is going the other way. But these species, titanium 3+ and copper 2+, are never perfectly octahedral. Okay, so now let's see what, so I showed you now in principle what a spectrum should look like. Let's show you some real data dental ceramics is an important application. Lots of laboratories generate new dental materials, and then the idea is to put on the calcium sites by substitution a small amount of copper and record the EPR spectrum. And you can see that the EPR spectra of hydroxyapatite and octacalcium phosphate are quite different, very different. So by analyzing these spectra can be analyzed, we can get parameters to it, and in both cases we learn actually that the axes are not perfectly coincident. It means we have a little bit of a distortion relative to the tetragonal symmetry. But again, the details are different in the ones. There's one more thing I want to like you take note over here. Here you see a concentration series from 0.01% to 10%. And you can see there's a systematic change in the spectra. And that's a very important aspect here, because the spectra are influenced not only by the local environments of individual isolated ions, but also by the interactions between two ions that are in some vicinity to each other, by the dipolar interaction and by exchange. And so it's always important when you measure EPR spectra to actually measure a concentration series, by systematically changing, and then you basically interpret the spectra of the isolated species only by extrapolation to a lowest concentration that you have. And if you don't have that available, then you need to do what you would again call a signal decomposition between the isolated the contribution from the isolated species, and then another component. You have to add another component due to the interacting species. Here, this is extreme. There are about 2,000 papers reporting EPR spectra of glasses. Many of them are not worth the paper they're printed on, because the spectra often look like this. So they're much too concentrated. So people make a glass, and then they have an EPR spectrometer somewhere, and they record a spectrum, and boom, it's published. And you don't learn anything from this, because these spectra are completely dominated by the inter-electronic interactions between different copper species in vicinity. So we have dipolar broadening, and in extreme case even spin exchange between them, and that gives a rise to these broad line shapes. So again, to bring home the point, we need to study the concentration dependence in glasses to get to the true value of G parallel and A parallel. So measure these spectra as a function of dilution. So here's some good data from the literature. They have respected this necessity. And here you see a typical experimental example and a simulation. When you look carefully, actually there is a problem here with the simulation. It's not really perfectly reproducing the experimental data. And I have to get to that. It has to do with the fact that in the EPR people call G strain and A strain, and which is similar to the phenomenon that Ben described before. Like there's a distribution of G values, there's a distribution of A values that causes line broadening. But the broadening effects of the G strain and the A strain on the spectrum are actually different. And to learn more about spectra like this, we need to go a little bit more into the details of how G and A are actually determined and influenced by the local bonding properties. This is another example, same thing. Let me go to this one first. Okay, so what do we learn from the parameters? There are simple formulas in the literature that arise from the use of application of perturbation theory that allow you to relate the parameter G parallel, yeah, and also A parallel to various parameters. The spin orbit coupling constant, which is normally held to be constant for a free copper 2+. There's a coupling coefficient, which is also P over here, which is also held to be constant. But then there are these parameters alpha squared and beta squared that you find here in the expression over here, which define bonding properties, the covalency of in-plane sigma bonding and the covalency of in-plane pi bonding. Yeah? And basically, from theory, you get this approximate expression, and alpha square, you can see here, interrelates both A parallel, G parallel, and G perpendicular. And what we learn from this is that that G parallel and A parallel don't vary independently, but they're interrelated from each other. There's also this parameter delta E, which is the energy of in the case of copper, of the B1G to B2G transition. And this one you can get from optical spectroscopy. So this parameter is actually available from a different method. You don't need this as a fitting parameter. Okay? So now I want to back up a little bit here. So let me illustrate some of the intricacies of the EPR spectra on a bioglass sample that was doped with 0.1 mole% copper obtained from collaborators at the University of Erlangen. Okay, here's the experimental data, and in red you see the superimposed fit. Yeah? So Claudio Magon took weeks to come up here with the optimal solution. There's a very, very careful fitting exercise. And yet, although the copper is so lowly concentrated, you see you have to include two components for the simulation, namely one for isolated copper and one for copper species in which the copper ions are interacting. You have still this green component, and only the experimental data you can only get to a fit with superposition of both. Yeah? Of course, this is the one that we're interested in. Yeah? And yeah, you then observe. Let me point out one particular observation that's very common in EPR spectra of copper in glasses. So you see here that on the parallel side, you see here the first peak is relatively well defined, and as you go to the other three peaks, the resolution gets worse and worse. The lines get broader and broader. Yeah? And this is a very specific example that shows you that this change in resolution actually is due to the fact that the A strain is a consequence of the A strain, so distribution of hyperfine coupling parameters. If it were only G strain, all peaks would be broadened in the same way. Yeah? You see only here, okay, but yeah, this would be no strain at all. You already see that here, this is a little bit broader than in the middle, but this is due to the fact that copper has two isotopes, 63 and 65, and you get them superimposed, and for the outer Siemens states, the difference is bigger than for the inner Siemens states. So this is well understood. Okay? Now you put a G strain only, then all of these lines would be broadened in the same way. This is not what we see. If you have an A strain, then it would be like this. Yeah? A distribution of A alone would be like this. The outer ones would be broadened even more compared to the inner lines. This is also not what we see. Yeah? What we see is this over here. Yeah? The lines get broader and broader from the lowest field to the highest field line. Yeah? And we see the opposite of this. And this means that actually the G strain and the A strain are correlated. So in a distribution in G, it automatically implies there is a distribution in A. Correlated in this case, which we don't see, and anti-correlated in this case, which we see. And when you look at different classes, this is a very nice review of EPR parameters analyzed in different kinds of matrices. You can see copper in phosphate classes, in borate, alumophosphate, borophosphate, silicate. Oops, sorry. Yeah. We can see here the anti-correlation. Now, I mentioned that the author here, Bogolomnova, actually did not assume any strain. Yeah? They simply analyzed the spectra assuming no strain at all and getting average coupling constants and average G values from the spectra. And you can clearly see that G parallel and A parallel are anti-correlated. So high values of G mean low values of A and vice versa. So it's basically this result that reinforces our interpretation of the spectra that the G strain and the A strain are anti-correlated, and that's why we see this different types of resolution in the different 4 peaks of the parallel contribution to the tensor. Okay. Yeah, to just give you a little bit of a EPR periodic table here. So again, this summarizes again what species you can observe with EPR. I showed you this on the list of tables already. And when you go to low temperatures, you can extend this a little bit here to include these species over here. At room temperature, it's limited to the green elements. In addition, through the hyperfine interaction using pulsed EPR spectroscopy, you can also observe indirectly the NMR, the nuclear magnetic resonance of these important nuclei that interact when they interact with electrons. Yeah? So you can see about half of the elements in the periodic table are in one way or another accessible to EPR spectroscopy. Okay. So application fields of EPR in glasses, redox processes, of course. It's very interesting to learn about manganese 6+ in glasses from Doris Mönke's talk. It'll be interesting. I don't think this has been characterized by EPR. Would be interesting to observe. But you see other things here. Ne? Chromium 3, chromium 4. Now, chromium 3 is the one that we can observe. Chromium 4 we cannot because it's a non-Kramers ion. Vanadium can occur in the 3+, the 4+, and the 5+ state. In the case of vanadium, we are fortunate. We can observe vanadium 5+ by NMR, vanadium 4+ by EPR, vanadium 3+ by nothing. They will basically have to we're limited to getting the 2 highest oxidation states. In the case of manganese, we can observe 2+ and 4+, but not 3+. And of course, we cannot observe 5+, but with EPR, we could observe 6+. With NMR, we can observe 7+, the permanganate, because that's diamagnetic. With iron, iron 2 and iron 3, cobalt 2, always the ones in green can be observed, the ones in black cannot be observed. So this is one application field of EPR, the characterization of redox processes. Defect creation by radiation, very important at modern application because people are increasingly using EPR glasses as containers for nuclear waste. So nuclear waste is radioactive, it creates defects in the glass structure, it changes the structure of the glass over long terms. It's very important to characterize the structural consequences of this radiation damage. So identify the species that are being produced, and also identifying the nuclei like boron, phosphorus, oxygen-17 that are affected, which we can do through the magnetic hyperfine coupling. Yeah, I've already mentioned luminescent glasses, optical glasses, neodymium, europium, erbium, and terbium are the ones that are the best candidates. I already mentioned dental glass ceramics, where we're using substitutional sites, vanadium 4+ and copper 2+ in particular, to characterize divalent cations in such materials by isovalent substitution, and also anion substitution in calcium phosphates, producing species like this. But the 6 important messages for standard EPR on glasses are you do require low dopant levels to avoid dipolar broadenings. So to make sure that you are at the lowest level necessary, you need to study a concentration series. But still, when you don't see a signal, it does not necessarily mean it's not there. The species isn't there. Because relaxation characteristics are important. Rare earth ions cannot normally be observed except for europium 2+ and gadolinium 3+. The rare earth ions are not observable at room temperature because they relax too quickly. We get into this lifetime broadening that Ben talked about. Heisenberg uncertainty limit basically makes this species unobservable. Then what you do, you need to slow down relaxation by go to low temperature. Yeah. Yeah. Quantification can be done in principle, but it's a laborious task. There are certain standards where you can relate the signal intensity to the concentration, and you add these to your samples as for internal calibration methods, standard addition method or something like this. Yeah. And without easy spin, without simulations, this is all not worth anything. So basically, you cannot publish anything today without having used easy spin to simulate your data. And computational chemistry becomes more and more important to relate your result, your experimental result, to hypothetical structures and environments. So basically the idea is you get a spectrum and then you simulate, you compute structures and compute using first principles to predict the G parameters and the A parameters from first principles, and then you compare. If you get a match, you have a good chance that your sample response reflects the reality and you interpreted your data right. Yeah. If you don't get a good agreement, it excludes the scenario. So a lot of things is done by exclusion these days. So you can eliminate lots of possibilities. Yeah. So in this sense, EPR is inferior to NMR, because in NMR spectroscopy it's always easy. Now, not always, in many cases very easy to read in the spectra and directly look at it and say, oh yeah, that's what it is. Yeah, this is the species. Yeah. In EPR, not so simple. Without the computational overhead, the conclusions are not totally certain. You need to always solidify your conclusions by computational chemistry. But EPR has more to offer by going to the time domain. So this is I will just talk about very briefly. It's a new, a recent development of the recent 20 years. You actually apply pulsed Fourier transform methods to record the EPR spectra instead of using this continuous wave technique. And basically, you are looking then at very broad lines, and the pulsed excitation window normally will only cover a fraction of the line shape. So in addition to this pulsed excitation, you will actually also have to change the magnetic field. And this is called echo-detected field sweep. It actually combines a field sweep, a change in magnetic field, with a pulse excitation. So you're actually recording the spectrum at different magnetic fields, but because relaxation characteristics are simple, you can do this quasi sweeping it continuously. In NMR, you would have to this would be very laborious, because you have to wait for the relaxation characteristics a long time and then go to the next magnetic field and so on. In EPR, this is done quasi automatically. A very powerful method called echo-detected field sweep. And I'll give you one example that we published some years ago, again with Pedro Donoso and Claudio Magon as the investigators, principal investigators. We looked at some photothermal refractive glasses. These photothermal refractive glasses have a rather complicated composition over here, yeah? But they contain, as is shown here in the sample B6, in the sample B5 and B6, they contain paramagnetic species, cerium, antimony, and tin. Yeah? And these potentially paramagnetic species, cerium, antimony, tin, also potassium bromide is in there, and without these dopants, the glass is actually not functional. They're not interesting. These photothermal refractive glasses obtain their properties by virtual presence of these species over here. So they're very, the photothermal refractive effect is one in which, by controlled irradiation, you can produce modulations in the optical properties. So these are actually materials that are being used for creating optical devices. So to understand what's happening in these photothermal refractive glasses, we looked at these 6 samples. The first one is just the matrix. Yeah? The second one, yeah, is the matrix exposed to ultraviolet radiation. Yeah, I forgot to mention. To produce these modulations in the refractive index and other optical properties, you need to expose these glasses to ultraviolet irradiation. So the sample B1 is just the matrix. Sample B2 is the matrix exposed to ultraviolet radiation for 20 minutes. So this is just a control. Yeah? Here, now we added silver. This is one important ingredient. But we're still missing these dopants over here. Yeah? So again, unexposed and exposed, B3 and B4. B5 and B6 is now the full glass, but unexposed. And B6 is the full glass now exposed to ultraviolet radiation. B1 and B3, the unexposed glasses gave no EPR signal. And here you see the full EPR spectrum of the exposed glass B6, recorded now in the echo-detected field sweep mode. Yeah? And what we see here is something extremely interesting. The top is the spectrum, the full spectrum, and you can see it has structure in it, and it also lies on top of a very broad background. The very broad background actually is the one that we observe if we only have the cerium 3+ species in there, which is basically the glass without the dopants, but without the tin and antimony dopants. And basically, this is just a manifestation of the cerium 3+ present. And here, the structured line shapes now are the isotopologues of antimony. Yeah? We have two different antimony isotopes that have magnetic moments, antimony 121 and antimony 123. And the total spectrum can be simulated as here. Here you see the simulation as a superposition of the two with their natural abundance and their well-known magnetic moments and spin quantum numbers, and you get an excellent fit to this. So this is the publication that we wrote on this. And you can see this is the spectrum simulated with the antimony interaction, hyperfine interaction. And on top, this broad stuff is the serum signal. Yeah. And then we can look at annealing. Basically, by thermal annealing, you eliminate the photorefractive effect again, and the spectrum, this very nice spectrum B6, starts disappearing. So in the annealing process, this antimony, this unpaired electron that is interacting with antimony, so it's probably an antimony 4+, is disappearing. So from this we could basically come to the following conclusion. So we have cerium3+ in the glass, but under annealing it produces cerium4+ and an electron. That electron is localized near the antimony dopant, producing antimony 4+ and gives rise to this particular EPR spectrum. But the antimony 4+ itself is not stable, and it interacts with silver to produce diamagnetic antimony 5+ and then silver nanoparticles. This is what's happening upon annealing. Yeah? And then it's these silver nanoparticles that nucleate the crystallization of sodium fluoride, which is held responsible for the photothermal refractive effect. So EPR could give some useful information on the initial stages of the photothermal refractive glasses. Okay, I very briefly would like to wrap up now. Very briefly like to mention another technique. This is called electron spin echo envelope modulation. Again, we are recording a spin echo here, and the spin echo, and record the intensity of the spin echo as a function of waiting time over here, t plus tau. Yeah? And basically the amplitude of the electron spin echo will depend on the time change over here. And here you see this plotted. And what's interesting is that when you plot the echo amplitude as a function of this waiting time between the pulses, you not only observe a decay, a typical relaxation as you would expect, but you also observe modulations over here. And these modulations are an independent source of information about a hyperfine interaction. And so by fitting this, stripping off the exponential decay and doing a Fourier transform, you get something like a free induction decay, and by Fourier transformation you get the frequencies of the Zeeman frequencies of the nuclei with which the electrons are interacting. So that's a very useful information because it tells you the unpaired electron is close to those nuclei. Yeah? And so this, we have used this as an source of information to analyze some rare earth doped fluorophosphate glasses. And here you see these electron spin echo modulated spectra. And we looked at here, this is very complicated glass compositions, the details don't matter, but we see here, compare here, a fluorophosphate glass that has as a component aluminum phosphate. And here we see a fluorophosphate glass that, in which the aluminum phosphate has been replaced by indium phosphate. That's the only difference, really. And what we see in the spectra is that when we replace it by indium phosphate, the fluoride component is much more intense. That is, the rare earth species now seeks in this indium phosphate the local environment of the fluorine. Whereas in the aluminophosphate, it is the phosphate peak, the fluorine signal is very weak, and the rare earth environment is actually more looking for the phosphate environment. So this, again, relates to the optical, can be related well to the optical properties, in which you would actually want want to favor the proximity of the rare earth ion with fluorine, not with phosphate. But that should be enough. So just to wrap up over here, when we want to look at luminescent glasses, we have a good magnetic resonance strategy involving both NMR and EPR spectroscopy. With NMR, magic angle spinning, we can resolve the local environments of the nuclei. With techniques like measuring dipolar interactions between the nuclei, REDOR, Markus will talk about it in the next presentation, we can get to the second coordination sphere. Again, now we can add EPR strategies to this. Again, if we study only the continuous wave spectrum of the EPR's active electron itself, we learn mostly about the atom itself. But if we combine this with electron spin echo envelope modulation, like I have shown, you learn something about the nuclei that are close, typically within about 1 nanometer. So putting everything together, you have a powerful new strategy that allows you to optimize glass structures as matrices for rare earth environments. Yeah. So with this, I'd like to thank everybody very much for your attention and look forward to some questions. Thank you.
Thank you, Helmut. I apologize, I said that you would talk us about NMR, but it's EPR, glass structure by EPR. Do we have some questions? This is a tough subject. And I think we should move on because we are running out of time. And then after, put together NMR and EPR opportunities to talk. Do you have a question? Okay, sure.
So thank you for your presentation. When you got to do your measurements under low temperature and got into the radiation with UVBs, ultraviolet, you irradiate at room temperature and then go down to low temperature, or the radiation is down at the low temperature? Room temperature, okay.
But apparently the glass will irradiate at room temperature, but then the species were sufficiently long-lived. We can only undo that by annealing, thermal annealing to 400, 500 degrees. But yeah, but in general, your concern is correct. To be really sure, one would be even more rigorous to actually do the annealing also at low temperature.
Okay. As we long far and far away trying to solve the structure of some glass, then we start needing to go in this more specific subjects and opportunities and experimental strategies. Nobody else? Yep, there.
Okay, Professor, thank you for your good presentation. I learned many things about the EPR. In fact, I have a simple but maybe stupid question. You give some samples about the oxyfluoride glasses. You know, after heat treatment, it will be crystallized. Is it possible to measure the local environment of rare earth?
Yes, of course. Yes. That would be very interesting to actually identify the phases to see where the rare earth ion is going, because many times you would actually be interested in the glass ceramics.
Okay.
Basically, to have the luminescent species. Ideally, the luminescent species would be in the crystallized phase.
Yeah.
And you exploit still the transparency of the glassy matrix.
Okay.
Yes, this would be certainly interesting, but we don't have results on this. Yeah.
Okay. After crystallized, the EPR spectra should be different.
Oh yes,
in glass.
the EPR spectra would be quite different for the crystallized glass.
Okay,
yes.
from glass and glass ceramics.
Mm-hmm.
Okay, thank you.
Thank you.
Okay.
Thank you. Yeah, let's go then for the next talk. Marcus will finally talk us about NMR, glass structure, solved by NMR.
Okay, thank you.
Thank you, Marcus.
Can you hear me with this microphone here?
Hello.
Hello. Let's see here. Hello. Alô, 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 aí. Aí, tá, agora, can you hear me? Yeah, okay. I think it's better than I have my hands. So, as Edu said, I will speak today about glass structure by NMR. So, I'll start with a brief introduction, and then I will speak a little bit about the NMR interactions and the ones that are relevant for solids. That's what it's the focus of the talk today. And then I speak about some NMR techniques and some results, mainly in glass systems, since it's a glass school. So the introduction, the NMR is based on the presence of a property of the nuclei, that's the spin magnetic moment, angular moment. And for those who doesn't know what the spin is, you can imagine that the proton is charged, and it's a sphere, and it's spinning. Then from this spinning of a charged sphere, you have a magnetic moment, that's the spin. The problem is that the proton is not a sphere, and it's not spinning, but anyways, we have this magnetic moment present. And for nuclei, we have many protons, and the magnetic moment we observe comes from the sum of all the protons we have in the nuclei. So depending on the species, we have different spin quantum numbers. So, and the magnetic moment is related to this spin quantum number by this equation here. So the magnetic moment is proportional to the spin quantum number, and the proportionality is given by this gamma here that we call gyromagnetic ratio. And this is different for every nuclei, so this is why NMR is element selective. So this magnetic moment will change for every species or every isotope you want to measure. And also the value of the spin, it's equal 1/2 for the protons, but for the nuclei it can be it can have many values, integer or half integer values. So the spin 1/2 ones are these ones that are represented here. So they are the easy ones. So in this chart here, we have the size of the balls here. It gives the abundance of each nuclei. And then the colors, they give how high the frequency or the magnetic moment is compared to the protons. So purple is very high frequencies, and the white ones are very low frequencies. So we have also the integer nuclei, so we have very few examples here. And the majority of the nuclei of the isotopes we have, they are half integer, they have half integer spins, so they are represented here. So the sizes of each symbol here gives the spin, so 3/2, 5/2, 7/2, and so on. And this is Helmut showed the NMR, the EPR periodic table. This is the NMR one. So it's black is good, so it's easy to measure. We can measure routinely. And then these gray ones, they are challenging. You can measure, but sometimes it's hard to get information from them. And this white dotted ones here, they are very difficult, and the white ones are impractical. So we like to work with these 3 here in our labs because we like to have some challenges. Of course, that we don't refuse to work with the black ones also. So a little bit of the theory. So I spoke that we have the magnetic moment associated with the spin. And what brings the NMR is the interaction of this magnetic moment with a local magnetic field that's created in our lab. So we have a big magnet there, I'll show here. So it gives this magnetic field B0 here. And we have an interaction of this magnetic field with magnetic moments. This gives us the main Hamiltonian, that's the Zeeman Hamiltonian. If we point this magnetic field to the Z direction, we have that this Hamiltonian will be proportional to the IZ component of the magnetic of the spin. And so then Hamiltonian is just like this. We can simplify this, taking these constants here, put all together in this omega 0 that we call the Larmor frequency. I'll show after how this comes. And then we have the eigenvalues of this Hamiltonian that are given by the spin angular momentum. So they can have values -I to +I. So we have 2I plus 1 levels. So if it's a spin 1/2, we have only 2 levels. It's -1/2 and +1/2. This gives us 2 different energy levels. So this would be, if you think classically, it would be the spin antiparallel to the magnetic field. We have a high energy state. And when it's parallel to the magnetic field, we have a low energy state. This happens, like I said, if the gamma is positive, what's not always true, but this is a detail. And then, of course, now we have 2 energy levels, we can do spectroscopy. Then we have populations here of these spin states, and then we have a difference in energy between these states. Then we have our spectroscopy. Now we have a frequency related to this difference in energy that's given by this constant gamma and the magnetic field B0. So here comes the element selective part. And B0 we can select as we wish or as we need. NMR has a very low sensitivity compared to other techniques. So this is an example. Without any magnetic field, both states are equally probable. But when we have magnetic field present, we have this case here. We have more spins in the lower energy level than in the higher energy level. And just as an example, for a 7 Tesla magnetic field strength for protons, if we have 20,000 spins, so 9,999 spins will be in the upper level, and 10,001 spins will be in the lower level. So I have only 2 spins of difference, and we can only do spectroscopy if we have this difference in populations that we call polarization. So the intensity of our signals is proportional to this polarization. The polarization is given by the Boltzmann equation. So this is a simplification of the Boltzmann equation to first order. Then we have this difference in populations proportional to the number of spins. So this gives the quantitative character of the NMR. It's proportional to the magnetic field. So if you want higher sensitivity, you go to higher magnetic fields. It's not always so easy. I'll show the size of the magnets for those who didn't see before. And it's inversely proportional to the temperature. So if you want higher sensitivity, you need to go to lower temperatures, which is also not always very experimentally feasible. So now I will give a vector picture of NMR that usually helps everyone to understand how this experiment is done. So when we have the spins in a magnetic field, they do this kind of precession here, this movement. And this precession is ruled by this equation. I'm not getting into detail. This is a classical equation of a magnetic moment in the presence of a magnetic field. And then if we get this magnetic field here and point it to the Z direction, we can select what the z direction is. So usually we put the z direction in the direction of the magnetic field. Then we have this equation down here. And the solutions of this equation, they describe this vector precessing around the magnetic field with this frequency here, that's gamma b0. That's our Larmor frequency. When you have many spins, of course, some of them are pointing up, some of them are pointing down. And in the sum, we usually have more of them pointing up. That's the lower energy state. And then we can measure macroscopic quantity. That's the sum of all these spin momenta together. So with this, and this is this magnetization here. That's the sum of all the magnetic moments in the sample. This is what we actually measure in NMR. So to measure it, we need to perturb this this magnetization, and to do so, we need to apply oscillating magnetic fields that are in resonance with this precession movement of the spins. So as these individual spins are precessing around the magnetic field, we can show also from the same equation that the magnetization is also precessing. And the most efficient way to disturb it from its equilibrium state is to apply oscillating fields. So this is where the resonance comes from in the name of the technique. So this is a chart just showing how this is done. So you see that in the beginning here, there's a small arrow rotating here. This is the applied magnetic field. We do this by putting the sample inside a coil, and we use this coil to apply this oscillating radiation. And then if we use this perturbation to bring the magnetization down to the xy plane, so z is the magnetic field direction, so xy is perpendicular to the magnetic field, then we have this situation here that we call a pi-half pulse. So we radiate the sample, then in the end the magnetization is in the xy plane. It's still precessing around the magnetic field as it should. What happens after is that we have this system is the magnetization comes from the sum of many spins, and they not necessarily have the same frequency in all spots in the sample, so they have a little bit different frequencies. So each one is spinning with a different frequency around the magnetic field, and then in the end, they lose coherency, and then we lose the signal. So this is more or less what's showing here. So they were all spinning together, but suddenly they start losing coherency, and then we start losing the signal until we have no signal anymore. So this is called relaxation, and this is why the NMR signal is what we call free induction decays. It decays. So this is more or less what a pulse sequence is. I will show some during the presentation. So whenever you see some block like this, it means I did something with the magnetization, either a pi-half pulse or a pi pulse, or there are some other special pulses that I will show, but it's usually like this. So for a pi-half pulse, we begin applying the pulse, the magnetization is here, so it starts relaxing, and it's always oscillating around the magnetic field. So what we get as a signal, if we put this, we use the same coil we use to irradiate the sample, we use to detect the signal, then we get this oscillating signal here that what we call the free induction decay. So this is more or less how the magnet looks like. So usually we need high fields, usually from 9 Tesla and higher. And so we need a superconducting magnet. This is why the NMR magnet looks like a thermal bottle, because this is what it is. We need to keep this coil inside here in very low temperatures, helium temperatures, so it keeps being superconductive. And then we need this cryostat to keep liquid helium inside here, some liquid nitrogen to isolate the liquid helium, and so on. And we do the measurements with a probe that's shown here and here that goes inside this magnet and brings the sample to the region where we have the strongest magnetic field. And the sample is shown here, so we have the sample inside this coil that we use to excite and get the signal back. So this is an illustration of the coil head. So it's an electronic circuit, so it's an oscillating electric circuit. These are the rotors we use. I will show after that we need to spin the sample to eliminate some interactions. And we have different sizes of rotors. We cannot read here, but for bigger rotors, we can go up to 5 kilohertz spinning frequency. And for the smallest ones that we have in the market, we can go up to 170 kilohertz when I put this figure here. But nowadays, they can go to 210 kilohertz. This is our magnets in our lab there. So more or less how the electronics of the experiment works, it works more or less like a radio transmitter and receptor. So to irradiate our sample, we mix a carrier frequency that has our Larmor frequency, the same frequency that the spins are processing around the magnetic field. And we apply our pulses. So we can have many different pulse sequences depending on what we want to do. I showed the simplest one, that's the 90 degrees pulse sequence. And these guys, they are mixed in a transmitter. This goes to the sample, and then we get the answer back. The answer comes as a sum of two different signals. One of them is the main interaction, the Zeeman interaction, that gives the same oscillation that we have here used to irradiate the sample. And we also have this other component here that gives the chemical information. It comes from the interactions that are perturbing the Zeeman, the main Zeeman interaction. And here is the information in this kilohertz. So we can say that this is the radio carrier, the radio wave. And here it's the voice of the guy singing there. And we want only the voice of the guy, so we use a receptor to remove this megahertz signal, and then we get only the signal of interest. So, as I said, we have the Larmor frequency. Spins are oscillating with this omega 0. And then we irradiate with the same frequency to excitate our system. And if we would get back the same oscillation, it wouldn't be fun. We wouldn't have any information. So the informations come from the different interactions that we can have involving the nuclear spins. So I got some examples here. So the Zeeman is the main one. The other ones, for high fields, they are usually much smaller, then we treat them as perturbation. Then we have the dipolar interaction, that's the interaction between two spins, I will show in detail. It gives information about distances. The J coupling, it's an interaction that's based on the chemical bonds, so it gives information about bonds. Chemical shift gives information also about bonds, but through the geometry of the electronic cloud around the nuclei that we are observing. So it doesn't really depend on these connectivities. And the quadpole coupling, that gives us information about geometry around the nuclei that we are observing. The quadpolar coupling is observed only for spins higher than 3½ Then I'll show only two interactions. They are the main ones. And I don't even have time to show the others. So the first one is the chemical shielding interaction. So the chemical shielding interaction comes from the magnetic fields that are induced by our local field on the electrons that are surrounding the nuclei. So we have electrons here. The electrons are moving. We have a magnetic field, so they create another magnetic field that usually opposes to the applied magnetic field. So here is an example of a benzene ring. It's a good example because we can imagine here how these electrons spinning in this ring here will create this local induced field. And we also can see here that if this ring here is pointing like this to the magnetic field, we have one induced field. You can imagine that it's a nice induced field, a big one. If we take this guy here and flip it perpendicularly to the magnetic field, you can imagine that the induced field will not be the same anymore. So if this induced field is not the same anymore, the total magnetic field that the nuclei is feeling, that comes from the sum of the B0 and the induced field is different. So it depends on the orientation. So the chemical sheet interaction will change the frequency of our nuclei. So instead of omega 0, we have omega 0 plus what we call chemical shift. And it's also anisotropic, so it depends on the orientations of our molecule relative to the magnetic field. So we can treat it as a tensor with different components, x, y, and z. So the frequencies will depend on orientation, following this equation down here, where this delta iso is the average of x, y, and z components of this tensor. And the delta here is the difference between the isotropic component and the z component. It gives us the information about how anisotropic this is. If the delta is 0, it means that it doesn't matter where the molecule is pointing, we have the same information, it's the same frequency. And eta gives information about the symmetry of this, this tensor. So it compares the x and y components. So if eta is 0, means that we have axial symmetry, x and y are the same. And if eta is different from 0, we have no symmetry or rhombic symmetry. And I call the attention to this component here. So this frequency depends on this angle between the molecule and the magnetic field, following this second Legendre polynomial here. I apologize to the French people if I don't know how to spell Legendre. Then what we see is if our crystallite is pointing like this to the magnetic field, we have one frequency. If it's pointing like this, we have another one. If it's pointing like this, we have another frequency. And when we have a powder, we have all of them together, like Helmut described before. Then we have what we call a powder pattern. So we have a line shape like this. So this line shape will depend on this delta and eta parameters. So if eta is equal, the figures were missing. So in the A here we have delta equals 0, and here we have delta different from 0. So here it's eta equals 0. That's the asymmetry parameter, and eta different from 0. And for phosphates, for example, the geometry of this powder pattern here gives us information about which phosphorus species we are looking at. So if we have Q0 species, all directions are equal. Now we have complete symmetry. So the delta is close to 0, so we have only a single line here. If we have one PO linkage to some other species here, then we have axial symmetry. Now we have only one direction that's different from the others. So we have an axially symmetric tensor. So if we have two bonds, then we have a rhombic symmetry. And also if you have three linkages, then now only the double bond here is the different direction, so we have axial symmetry again. So we can distinguish between different phosphate units just by looking at the spectrum. So the dipolar interaction, I'll go a little bit fast in the dipolar interaction because I will not have time to go through it in detail. So, but this also perturbs our energy levels. And the perturbation Hamiltonian, they are given here. And we also have the same angular dependence here, 3 cosine squared theta minus 1. That's the second Legendre polynomial. And how it perturbs the energy levels is shown here. So dipolar coupling only shows when we have a pair of magnetic momenta. So it's a magnetic-magnet dipole interaction. And then we have here the energy levels for a spin pair. And this is how it's perturbed when you have the dipolar coupling. So you see that this difference in energies here, they bring together this angular dependence here. So if this spin pair is pointing perpendicular to the magnetic field, we have a case like this. But if they are pointing in other directions, we have other of these doublets. It's doublets because we have always two transitions here. So we have a powder pattern that looks now like this. So it has these two horns. This if we are considering two spins, 1/2 interacting. But when we go to two glasses, we have a distribution of these distances. Then we have something like this. Now we have a completely, we lose completely this powder pattern here, and we have a single Gaussian representing this distribution of dipolar couplings. But anyways, this distribution can be represented by a squared average that we call the second moment. That gives us some information about the average dipolar couplings that we have in the sample. So it comes from structure information that comes from the sum of 1 divided by the internuclear distances to the power of 6. So if we can measure this second moment, we can have an average information about what's happening in our system. So now the quadrupolar interaction comes when we have nuclei that have spin larger than 1/2, so 3/2 and higher. And this, what happens for this kind of nuclei is that we have a quadrupole moment intrinsic of the nuclei. It's as if we have the nuclei has a ellipsoidal shape, and then it's as if we had, compared to the spherical nuclei, we have less positive charges here and more positive charges here, so we have this quadrupole here. And this quadrupole interacts with electric field gradients in our sample. And this electric field gradient comes from the neighbors. So we can characterize this interaction by a tensor like we did with the chemical shielding. And this tensor can be characterized in its diagonal form by 2 parameters because it's a symmetric tensor. So you only need the CQ that gives how strong this interaction with the electric field gradient is, and eta that gives us the geometry of this electric field gradient. So in the simplest case, that's a spin 3/2. So we have a single spin here, but we have 4 levels because it's a 3/2 spin. So we have here different transitions. So we have the central one that's represented to this central line here. And we have the satellite ones, that's this small frequency and larger frequency. So we have one transition here and one transition here. But what defines this omega Q1 here is also the first Legendre polynomial. So we also have the same powder pattern here, but we have 2 summed up. We have one powder pattern here, one here, and the central transition is not perturbed by first order. But usually the quadrupolar coupling interaction is stronger. It's strong enough that we need to consider second order perturbation theory. Then when we go to second order, we have this kind of perturbation of the energy levels. Now the central transition is also perturbed. And the perturbation is given by this omega Q2 frequency here. That's given by this equation down here. So this equation gets angular contribution from second Legendre polynomial, but also from the fourth Legendre polynomial. So this will be important when I speak a little bit about magic angle spinning. So what happens is that now we have a very complex line shape. So only looking to the central transition, we can have all these line shapes here for a single species. So things get a little bit more complicated to be analyzed. And in glasses, we may have many of these contributions all together. And in the end, we have a broad spectrum given the distribution of quadrupolar coupling constants. We have methods to analyze these distributions. It's called the check distribution analysis, the check distribution model. But we are going to speak briefly about this. So now I'll show some examples on how we can apply these NMR techniques for the study of glasses. So starting with ionic conduction, so we can study how the mobility of the ions in our systems. So this is work where we analyzed these systems here, this borophosphate system with lithium, potassium, and cesium. More specifically, I analyzed the lithium mobility in these systems. So when we have very low temperatures, so it's down here, we have a broad spectrum because lithium is all in fixed positions, and they have dipolar coupling interaction one with each other. Then we start heating the sample, and then what happens is that we have a narrowing of our line. And this narrowing is because now we have movement of these lithium ions, and then the dipolar coupling is averaged to a smaller value, so this is why we have this narrowing here. So when we analyze the narrowing, we can get activation energies to this mobility, and then we can compare with what's happening in other techniques. We can also study the distribution of ions in our system. To do this, we need to measure the dipolar coupling interaction in our systems. And to measure this dipolar coupling, we can use a pulse sequence that's called the spin echo or Han echo sequence. It works like this. We have a pi half pulse here, I have shown before. So the magnetization is now on the XY plane. And then we start having this dephasing of the spins. And then after some time that they are dephasing here, so you see that these dashed guys, they are going counterclockwise, while the solid lines here, they are going clockwise. Then I invert them. I apply a pi pulse, so everyone's like this, they do like this. But the ones that were going counterclockwise, they keep going counterclockwise. But now they are in the other side here. So they are going this direction here, while the others are coming clockwise direction. So they meet each other again, and we have what we call an echo here. So if we wait the same time that we waited here, we wait here, we have this echo here. So this is like these runners here. So the blue one runs faster than the others. So they are running. Then I apply the pi pulse. I tell everyone to come back. And then the same time that this guy took to go from here to here, he takes to go from here to here. The same is true for the green and red guys here. So they come here at the same time. So this is the echo I'm showing here. But the echo is only formed if during this time here, I have the same Hamiltonian that I would have during this second time here. Problem is that when I have dipolar coupling between like species, they are the same species, when I apply a pi pulse for one of them, I apply a pi pulse for the other also. Then the dipolar coupling contribution from the neighbor is changed in the second period here. And then when we have high dipolar coupling interaction, this echo here will not be formed, or it will decay with this time tau here. This is what more or less we see here. So we apply a pi half pulse, then a pi pulse. And then if we measure the echo now as a function of time, it will decay. And this decay is proportional to the second moment that I showed before. That's a quantity that relates to the dipolar coupling, the average dipolar coupling interaction in our sample. So in this way, we can measure dipolar couplings by measuring how this echo decays. So when we take this curve here, it decays as a Gaussian, and the second moment is given as a parameter in the Gaussian. And then we can measure this parameter for different systems. So this is an example for two different systems, a sodium silicate glass and a sodium borate glass. So you see that the second moment increases with the concentration of sodium, which is expected. So I have more sodiums, one close to each other. So the second moment should increase linearly if we have a random distribution. But you see that in the other system, when you go to these concentrations here, we have a saturation of this second moment. So it doesn't change. It means that the sodium, they are clustering together. So we have proximity between it's not a random distribution. And now we have clustering of the sodium ions. The same thing can be done when we have unlike species. So I said that in these two tau periods, if the Hamiltonian is the same, the echo is formed again. But when we have unlike species, I apply the pi pulse for one species, the other one stays the same. So this decay of the echo doesn't bring information about the heteronuclear dipolar interaction. So to get information about unlike species, about heteronuclear dipolar interaction, we do two different experiments. So we do the echo experiment, the normal one we were doing. This will decay with the homonuclear dipolar coupling. And at the same time, we do a different experiment. At the same time that we apply a pi pulse in the S species that we are observing, We also apply a pi pulse in the neighbor species. So we need a 2-channel experiment to do that. And then in this case, when we compare these two signals, I can remove the information about the homonuclear dipolar coupling and keep only the heteronuclear dipolar contribution. And then we can measure second moments for unlike species. Then we can also get information about proximities. So this was done by Helmut for lithium systems. So it's comparing with lithium-7, doing double resonance experiments between lithium-7 and lithium-6. They could measure these second moments for lithium in lithium silicate glasses and also lithium borate glasses. So we see again in the silicates we have this clustering of lithium ions, while for borate glasses we have a random distribution of the, so if the second moment changes linearly, then just remembering, then we have a random distribution. While here I vary the concentration, the second moment keeps the same, so it means that we are having clustering. Then for alkali silicate glasses, usually we have clustering of the ions, while in alkali borate glasses, we have usually random distribution of the alkali ions. So to analyze the short range order, we go for chemical shift information, usually. We can also analyze our network modifiers, just selecting to which species we want to look at which time. So we can have information about the neighbors that are directly bonded, the coordination numbers, if the species are one of the black ones there, and site quantification. So, but the problem is I'm looking to a system that have many, many interactions all together. I've shown 3 of them, but we have all these interactions here. And then most of them are depending on the same parameter. So what we do, we spin our sample in an angle that makes this parameter go to 0 in average. So now every interaction that depends on this parameter, they are simplified. So dipolar coupling goes to 0. All the other interactions, the chemical shift goes to isotropic. And the quadrupolar coupling goes to second order because we have that fourth polynomial there that's not averaged to 0. And then, but anyways, we have a simplification of our spectrum. By spinning the sample, we introduce some periodicity in our signal. So the signals are usually like this. We have these rotational echoes that we call. And when we Fourier transform, we have what we call, we have a central line here. And then we have this, what we call spinning side bands. And the spinning side bands, they mimic more or less the static spectrum. So we can get also information from these spinning side bands. So as faster as I spin, as further away the spinning side bands are, and more site resolution I can have for the studied system. So fast rotation is good when we want to differentiate between different sites that are too close together. So this is an example of magic angle spinning of silicon species. So we can detect just by the positions here what is a Q4, as a Q3, Q2, and Q1 species. So Rafaela has shown before what the Q species are, so I'm not getting to detail because of the time. This is an example of a pure network former glass with phosphorus and silicon. So I have a mass spectrum that looks like this. It's a single line for all the compositional series. But from the silicon spectrum, we have different stuff here. We have 6 coordinated silica species. And the 6 coordinated silica species would require Q0 species, phosphorus species interacting with it to exist. But we are not seeing this in the phosphorus spectrum. So we went for static NMR. So to get information that we were losing with the mass, spinning, we lose information about anisotropy. And I showed in the beginning that for phosphates, we can identify which species we are looking at just by the anisotropy of the line shape, or of the interaction. So we see that when we start having this silicon 6 species, in the static spectrum, although I cannot see anything in the mass, I can see that I have 2 contributions, one axially symmetric one, and one isotropic one. So it's the P3 and P0 units, and then from these complementary experiments, we can identify these species. So as I said, for the quadrupolar coupling, we can average out the first order, but not the second order that comes from with the first polynomial that's given by this dashed line here. They have no common roots, so we cannot average out both together, although there are some crazy techniques for that. And then if we look for a bottom spectrum, for example, we have that for BO3 units, they have this trigonal geometry. So we have an electric field gradient that's different from 0. Then we have a powder pattern for a single BO3 unit here. While for BO4, it's a symmetric unit, then the electric field gradient is close to 0. Then we have only a Gaussian here, like we see in other systems. So for borates, we can differentiate between B3 units and B4 units, just looking at the shape of the line. But because of this low electric field gradient for B4 units, sometimes it's hard to separate these units. As in this example here, it's a molybdenum borate material. And then we have here a BO3 unit that comes from impurity in the sample, and 2 B4 units that comes from the crystalline structure. And here we can, again, get information about anisotropy by looking at the spinning side bands, that they still preserve the line shape that we would see in the static spectrum. So by observing the spinning side bands, we could differentiate between these two different species and then get to this fitting here. So this is a double approach. So we have to fit this spectrum and this one with the same parameters, and then we could get nice parameters for these two borate species. So for bottom, you see that we have this nice quadrupolar powder pattern. This is because the BO3 units, they are very rigid. So every BO3 unit in the sample, they have the same electric field gradient, more or less. We don't have a distribution of electric field gradients. For aluminum, it's not the same. The distance between aluminum and oxygen, they can vary along the sample, distance and angles. So we have distributions of environments for the aluminum. And then what we see is a sum of all these quadrupolar powder patterns that could show up, come from these different electric field gradient interactions, quadrupolar interactions. So for aluminum, we can still differentiate between aluminum 6, aluminum 5, and aluminum 4 species. But they have this line shape that you see, it comes as a Gaussian in this side, but it has a long tail in the other side. This comes from this check model that I mentioned that models these electric field gradient distributions. So although I can say that I have aluminum 6, aluminum 5, and aluminum 4, it's hard to quantify because it's hard to say where the sobreposition is, if this one is broader, it's a little bit narrower. So to try to resolve this kind of problem here, we go to the second dimension. So we have experiments that can be used to correlate between this spectrum that I'm observing here in one dimension, that's this dimension here. And in the second dimension, we have a excitation of triple quantum in the system here. I will not explain in detail, but we can resolve in the second dimension isotropic spectra here. So these guys here, they are not more, doesn't have any more these asymmetric line shapes, but they are all symmetric lines. And then in this way, we can resolve the parameters for the 3 components and do the quantification of the aluminum species. So now going to the medium range order when we are trying to investigate distance between neighbors, mainly in the network formers. I will give you as an example this system where we have a borophosphate doped with zinc. So as I increase the zinc concentration, we create more of these B3 units. And we have variations in the B4 units here. But it's hard to say, only looking at the spectrum, what is this B unit here? Is a B unit connected with 3 phosphorus, with 2 phosphorus? What's happening? When we look to the phosphorus spectrum, we have very low resolution. It's hard to define the different components here. But of course, we can also see the tendency here. So when we have more boron and more zinc in the sample, this line goes to the left. Then what we do, we start digging information from different types of experiments. So one of the informations I can get is information about coordination between phosphorus and phosphorus species. So for this, we use this experiment that's called refocus inadequate. So it's based on the excitation of the double quantum transition. That's the transition from here to here. It means that we have the two spins pointing up, and then I flip both together down in a coherent way. So it only happens if they are interacting with each other through the J interaction in this case. So translating, if I have a signal here, it's because I have a POP linkage. If I don't have a signal, it's because I don't have a POP linkage. I have an isolated phosphorus unit, or the phosphorus is coordinated with boron or some other species. So here we can see the double quantum filter here and the normal spectrum. Then by comparing, we can say that this central component here doesn't have a POP linkage because it doesn't show up here. So by this simplification of the spectrum, we can start making some deconvolutions of our signal. Of course, we can also get information from heteronuclear dipolar coupling. I will not have time to explain this in detail. So it works more or less like the CDOR experiment, but for rotating samples. So because we are rotating, these pi pulses that I applied for the CDOR I showed before, I have to apply one of these pi pulses for every half rotor cycle. And believe me, it brings back the dipolar coupling interaction that we are removing with the spinning of the sample. And we have, when we take the difference between signal without the pi pulses in the second species and the signal with the pi pulse in the second species, we have a signal like this. So it's a different signal, so it means 1 means that they are completely different, and 0, they are not so different. If we analyze the beginning of this curve, we can again get information about second moments. That's the structural information we are looking for. So doing this for this boron phosphate system, we can select, we can measure to how many phosphorus the boron is connected, and then we can make attributions here, and then come up with the speciation of the system. So just the last technique now, when we have very broad lines, this white and white dotted points in the periodic table I show, the difficult and challenging ones, usually they have really, really broad lines. So we can use special pulses to measure these samples that are pulses that sweep the frequency. So we can excite a broad range of frequencies with one single pulse. So it's called wideband uniform rate smooth truncation. So of course, they come up first with the acronym here, the Wurst, versus sausage in German, because the pulse has this shape here that in the head of some guy looked like a sausage. I don't know. And so the idea is that we can measure really broad spectra, like this one is with tellurium that comes from 3,000 ppm to 1,500 ppm. So I can measure these really broad regions. Here we have measured magnesium in glasses. So from MS, we have this complicated spectrum. It's hard to simulate this line shape. Then to get some confidence about our parameters, we went to the static spectra again. But here the static spectra are really broad. Then we had to use this kind of pulses to excite the whole spectrum with a single pulse. And here, these Wurst pulses, they are also very good for saturation of transitions. And saturations happens, I have an example here. So I have a spin 5/2, that's magnesium. And let's say I have this transition -1/2 to -3/2. So the populations here, they are following more or less the Boltzmann distribution. And with these Wurst kind of pulses that I've shown before, we can saturate transitions if we apply them for a very narrow frequency region. Let's this satellite transition here. When we apply the pulse, what happens is that saturating means we have a population going to 0 here. So we have equal population, these two levels here. But if we look to the central transition, I have increases the population of the central transition here. So now I can enhance the signal just by applying these Wurst pulses to saturate the satellite transitions while I observe the species of interest. So just to end, then I put together again this slide that Helmut showed in the beginning. So here it's a redoor between scandium and phosphorus. So when these curves go too much up, it means that the scandium is interacting strongly with phosphorus. So these curves too much down here means small interaction between scandium and phosphorus. So you see that for this sample with aluminum, Helmut shows this EPR spectra here. We have a very small fluorine signal for ytterbium, and then by replacing ytterbium by scandium, so we would be able to do NMR. We see also that the scandium is coordinating with phosphorus preferentially. So this both experiments, they are saying the same thing. The rare earth is, the coordination environment of the rare earth is rich in phosphate species. But when we replace aluminum by indium, then the EPR shows a strong fluorine signal. It means the ytterbium is close to the fluorine. And also the scandium phosphorus redoor show no dephasing at all, meaning that also the same thing is happening with the scandium. They have similar chemistry. Scandium is going to the fluorine region, what we could show also with fluorine scandium redoor. So just as final remarks, the NMR is element selective, so I can always select to which element I want to look at which time. The spin interactions perturb the energy levels. This is what brings information to us. We can select interactions of interest by selecting different pulse sequences. So I can use different interactions to get different types of information. And here what I have already said. We have information about the nature of our species, chemical bonds, distances, coordination, geometry, and so on. So this is our group, and then thank you very much.
Okay. Thank you, Marcos.
Also 5 minutos.
And well, we have a lot of time for questions. You can make all the questions you want. Yes.
Thank you for your presentation. I have one maybe a bit basic question, because on those spectra, the y-axis is magnetization.
The y-axis is as the intensity of the signal.
And this ppm, how do you interpret this value? Because it's I have never done NMR, so it's a bit new to me.
This ppm is like, usually we have a magnetic field there that we say 9.4 Tesla, but it's 9.4002 today, and tomorrow it's 001, and in the other day it's 0005, and so on. So we never are completely sure about the value of the magnetic field. So we don't measure absolute frequencies. We measure relative frequencies. So we have some model compounds. We know, use them as a reference. And then all the signals we measure are compared to this reference. So ppm means this is like the parts per million. That's how different these two frequencies are relatively to each other.
Thank you. So a bit like Raman shift, in a way that it doesn't matter what the initial strength was. And
yeah, also, you imagine different magnetic fields, you have the same ppm values there.
Thank you.
Yeah.
Somebody else? Yeah, yes, yes. So, I think we should go to have lunch.
People are hungry.
Thank you again, Marcos.
Okay, thank you.
If you want to talk about more NMR, EPR, the professors will be here around to the end of the week, so you can stop and talk with them all the time, okay? Then, thank you. I guess you have a 1 hour lunch and go back to the hotel fast to take the bus there for the visit to Lamave and UFSC this afternoon. And people that are not hosted in the hotel can also go there to take the bus, okay, and take this opportunity to visit La Mave, okay.